All right. Good morning, everyone. I think it's 9 o'clock, so we can start the tutorial. I'm Mohit. I'm the second guy there in the picture. Unfortunately, Professor Gassan could not make it today. He was taken ill like a few days before, so he had everything booked, but unfortunately, he was not able to attend the conference. But I'll try to do the entire thing myself. It's going to be a 3-hour tutorial, but there's going to be a 30-minute break in between, which is great, which is fantastic for my voice and stuff. So we'll start now. We'll take a break at, I think, 10 o'clock. And then 10 to 10:30, there's going to be the break and we'll start back again. Hopefully, I'm planning to complete it before 12 o'clock or 12:15 to allow at least around 15-20 minutes for any questions. And I don't want this to be a very formal thing. So, if anybody has any questions in the middle, just feel free to stop me and we can have a discussion over there as well. And I believe there's a virtual component and people should be able to see all this. If anybody has any questions, you're more than welcome to put it in the chat and I'll try to answer either during the break or after the tutorial is done. With that, we can start with the tutorial itself. It's going to be about robustness at inference. 3 components that we'll discuss: explainability, uncertainty, and intervenability. What these 3 are, we'll go through them one by one in different parts. Specifically, I think intervenability is something that's going to have multiple definitions, and we'll talk more about it when we come to that. Explainability and uncertainty is a bit more straightforward because there's been a lot of research that has already been done on these topics. So I put the slide before, but all the materials that I'm going to talk about right now, it's on the website. On this particular website, you can also find it in the WACV, the booklet that you were given as well, and online thing, the QR code specifically. You'll be able to go to this website where we have all the slides listed as different parts. So with that, we can start off with, I always like to start with memes. And the first meme that we'll start off with is this, where expectation versus reality of what deep learning is. So when you're a fresh new student who comes in looking at deep learning and thinking, okay, this is something that I want to do in life, your expectation of what it is built up by media is very different to what you'll actually see when you first start training your models, when you first start working on these deep learning architectures. And we'll discuss about why today, and specifically a small component of that, which is the robustness piece of it. This was a very famous figure a few years back, where just looking at the images on the right-hand side, it looks very much like this idea of, is it a puppy or is it a muffin? It's a blueberry muffin or it could be a puppy as well. And it wasn't, you have to take a few seconds just to see these images, just to make sure that what you're looking at is actually a puppy and not a muffin, or vice versa as well. Just a fun fact, the newest ChatGPT, if you put this image, it can correctly classify everything. So it's a bit redundant right now. But the point is that we can come up with these kind of naturally adversarial kind of images, which is very hard for any kind of a state-of-the-art deep learning module in order to give you these kind of good solutions. And simple things like taking a stop sign and rotating it, shearing it, is going to cause problems to the network as well. These are well-known domain adaptation or domain problems that exist within neural networks. And everything is basically this idea of expectation of versus reality. We are not getting what we expect from deep learning in a lot of these situations, especially when the data is different from the testing data is different from the training modules. So the very famous quote, just adapted for us, which is that the best laid plans of sensors and networks, they often don't go as you planned it. So what is it that we require from deep learning algorithms, especially at inference, is the question for us. We want our deep learning enabled systems to predict correctly when there's novel data. And this idea of what novel data is very, it's not always clear what the definition of novel data is. We can think of it as multiple sources, right? It could be from a different distribution. It could be some kind of an anomalous data, out of distribution, adversarial, corrupted data, And we'll talk about all these things, especially except the new classes part. We'll talk about all the other ones during the tutorials. You might look at this and you're thinking that it's all different applications. If you look at papers, they try to solve test distributions as domain adaptation. They try to solve anomalous data in terms of anomaly detection, out of distribution data as out of distribution detection, and so on. So each of these small factors, I call it small, but there's a huge amount of work out there, literature out there that is trying to look at these, define these novel sources of data and use it to show the robustness of neural networks and deep learning algorithms. So on the right-hand side was this very famous German dataset paper on traffic sign detection and recognition. We took that data set and added these kind of simple noise onto it. So currently, what you saw was blurred noise. What you're currently seeing here is some kind of codec distortion that was there. In this case, there's the color photographs, the color images are turned into black and white. All these noise, all these distortions, if when you're training your data set or your networks on pristine data, works extremely well. But as soon as you add these kind of distortions and noise, and these are something that are naturally occurring. These happen in real life. You have dirty lens. You have some kind of an impediment on top of your lenses. These things happen in real life. How can we make our networks that was trained only on pristine data? How can it be more robust is what we are trying to answer here. And that is a very important requirement from deep learning algorithms. We want them to properly and correctly recognize on novel data. So the first thing that comes to our mind when we think of there's novel data, we want to have a more robust and a better prediction, is saying that we want to have a good training module. We want to make sure that we integrate all this data within the training module itself. But it's not always a good thing to try to overcome these challenges at training. So let's talk about part one of this thing, which is how do we overcome these novel data during training? That is, let's say we had access to these anomalous data during training. How and where and when would we use it? Let's say I'm starting off by using it in the beginning. That is, I have a huge amount of data in the at the start before training a model, and I have a small amount of novel data. Now, if I include that small amount of novel data within the training data set, it's not always a good thing, because just look at this image here, for instance. So let's start by actually training a particular module. This is a toy diagram, but we do have this particular paper at the bottom basically goes through this and tries to understand from an active learning setting what is happening. But essentially what we found out was that more easy the data is, it's very easy for a neural network to train better in the beginning stages. That is, when I say easy, we look at it more from an information theory point of view. If the amount of information in your training data is low, then that means a network can easily kind of configure itself and get a good classifier. That is what we see here in the top. I hope you can see the cursor. Perfect. So if you have the top where, let's say in an active learning setting, where you're using small amount of data to train your model, I'm only using these red highlighted regions for doing the training. So you have these two clusters here. You have this cluster here on the left-hand side, and you have cluster here on the right-hand side. Now, both these clusters have their own different class of data. And let's say I have 2 points from the cluster on the right and 2 points on the cluster from the left. It's very easy and simple to see that my classifier can easily recognize and distinguish between these two things. But let's say that I was not looking at these things in the middle. I was looking at the most uncertain data, which is going to be somewhere here. So I have only access to 2 data points from each class. So it's this and this for the left class, while this portion here and this one here for the blue classes. And if these are the only data that is available, you'll see that my classifier is going to be completely different. The performance is going to be very, very bad. So this tells us that if you use uncertain data during training, especially in the initial stages, or I'm using uncertain, but it's actually novel data during training in the initial stages, it is not a good idea. Our performance is going to be even worse, and you might never actually recover. You might not be able to, and if you're doing this in an active learning setting, you might never be able to recover a good performance when in the initial stages you don't have good or low information data to start off with. Now, if you think the opposite is true, that, okay, let's train everything in the beginning and let's use low information data, like normal, good, pristine data to start with, and then introduce novel data at the very end, what you'll encounter is catastrophic forgetting. That in this particular image, what you see is that in the initial stages, your network was trained with a simple MNIST dataset. It was performing exceedingly well, almost close to 100. After a certain epoch, in this case 50, you add a different kind of a dataset, an FMNIST dataset, and you train with the fashion MNIST dataset. The network that had learned the simple digits from MNIST kind of forgets what it has already learned, so as to make space and to make more complexity for the newer data set, which is the fashion MNIST that is there. And this is an issue because you don't want your network to forget what it has learned. You have spent considerable amount of resources in order to train this network. So it's very important that a network does not forget anything and everything that it has forgotten, anything it has learned from before. Of course, there's a lot of work right now that tries to overcome this idea of catastrophic forgetting, but the point still stands. It is not always clear when and how to use novel data during training. In fact, I like to think of this as like a 1-2 punch that novel data provides the network itself. Novel data may not be available during training. I think by definition, if something is novel, it might not be available during training. So even if available, novel data does not easily fit into either the earlier or later stages of training. Also very important. You don't know when and how to include this kind of novel data. So, and especially in an autonomous vehicle setting through which I was introduced this kind of a problem, it's not always clear when and how to use these kind of this accident data or novel data during training phase. So what we'll be advocating for today is that we have to handle this at inference. That yes, you have a network that has been trained on pristine and good data, but when you're testing, you will encounter novel data, and you have to make some kind of changes either to the network, the features, or something else in order to make a more robust prediction. And that is essentially what we'll be talking about. We must handle novel data at inference. So the title of the tutorial itself, which is Robustness at Inference, is derived because of this. We want to know where and how to use novel data or to predict on novel data, and specifically, it has to be at inference. This actually was a stop sign you would have seen all the time, but if you go to national parks, you'll see green stop signs. So this is something that we encountered in Alaska, actually, and I'd taken a photograph at the time. But this kind of stop signs exist in Alaska, and it's not always clear how a network which has always been trained on this kind of a red stop sign, how it works on top of these kind of green stop signs, which exist in real life scenarios. There's also, of course, the famous black swan incident. It's a completely different thing, not something I would talk about in this particular scenario. So with that, we will talk about the objective of, we have discussed what the objective of the tutorial is, which is to discuss methodologies that promote robustness in neural networks at specifically inference. So we'll divide this into 5 different parts. The first one will generally talk about inference and give a very brief introduction to neural networks, and more importantly, from an information theoretic point of view, what exactly is happening. And then we will discuss explainability, uncertainty, and intervenability. So all 3 things, hopefully before the break is done, I'm hoping that part 1 and part 2, that we'll be able to complete these 2 parts. And once the break is over, when we come back at 10:30, we'll have uncertainty and intervenability, and we'll also conclude, which is going to be part 5. So we do have a lot of things to cover today. So let's start off with the first one, which is inference in neural networks. So the goal is to just very quickly go through the neural network basics, and then very quickly discuss what we mean by robustness. We'll specifically talk about recognition and classification experiments, and we'll have a more theoretical understanding of the information that is available at inference and some kind of challenges and how we plan to tackle them, which is the availability and utility of gradients. So neural networks, I think all of us know what neural networks are. Essentially, given some kind of visual data or any kind of data, it's able to extract some very simple patterns out of the data and combine it in non-linear ways and hopefully give you a very good prediction of what this data was. Either it could be from a supervised fashion, self-supervised fashion. In any case, you usually have these kind of three modules, which is low-level features, mid-level features, high-level features, and then you can use these kind of features in any task that you want later on, either from a generative perspective or from a supervised classification perspective, discriminative perspective. You still have access to these modules and layers. The basic component of a neural network, again, extremely simple. It's just a single input that is going into a neuron. A neuron is nothing more than an aggregator. It has a summation of all inputs that is coming into it. And there's a simple nonlinear function that happens. In fact, this one I think is a sigmoid function. Right now, it's the most popular one at present is even simpler. It's either a ReLU or a leaky ReLU. So very simple nonlinear processes happen within the neurons, and even the summation part as well. Very simple. After this, of course, you have quite a few architectural changes that can happen. You have ResNet architectures which go all the way back. You have TenseNet architectures, but essentially the basic building components are still extremely simple neurons. So of course, you then combine these neurons, you stack them up, and you put them into different layers. And once you do that, you'll be able to get a good classification. Hopefully, given this image of a cat, you will be able to get the output as a cat at the very end. All the hidden layers is essentially what we discussed, which is that your representations that you get, the lower layer representations, the mid-layer representations, as well as the high-level representations are all going to come from this hidden layers that exist within a neural network. The reason I bring this up is because right now, the changes that have happened has been immense. Like 2011 was when AlexNet and ImageNet came out, but then in a brief span of about 12 years, the changes that have happened in neural networks has been extensive. Before, we used to think of them as modules that help us in getting some predictions. But right now, just trying to understand the statistics of a neural network itself is that conferences which basically are designed in order to try to understand the representations that exist. This is from a parameter perspective. Currently, the GPT-3 I think this was 3, but the GPT-4 architecture that came out has 1.76 trillion parameters. It is huge, and I mean that statement does not do it justice. It's impossible to try to understand the scope of this architecture. And looking at them as neurons and stacks of neurons is not something that is feasible for us to do. That has to be something else. We have to be able to have different concepts that we will use in order to try to understand these different architectures. So that was a very basic overview of neural networks. Hopefully, I'm assuming that everyone is familiar with neural networks, because what we discussed in the last 2-3 minutes is nowhere near sufficient to try to understand neural networks. The goal was to actually come to the last slide, which is that it's not possible to do element by element analysis of these methods. So given these kind of deep learning, and let's say that it has already been trained, which again is itself a big thing, but let's say it has already been trained. You have access to huge clusters, you have access to the best GPUs, you have access to AWS servers. And once you have that, you'll be able to train your networks. And once you have trained your network, let's say all you want to do is give this image of a cat to the network and see what the output is going to be. Hopefully the output is going to be the same, which is that, with 89% confidence, or maybe hopefully about that, you will get your output as a cat. Now, let's say there is a network, this particular network has been trained on all natural images, on all cat data, dog data that is out there. In that case, this is not novel. If X belongs to the training data set itself, the data is by definition not novel. Now, let's say I make a small complication on top of this, and instead of giving the same cat, I give the image of cat from last year's movie. Actually, this is 2024. I think it came back like in 2022, which is Puss in Boots, basically. So this image, if you give to the network, now this image of a cat, also a cat, but it's an animated figure. Maybe it's not in the domain of the network. What I mean by that is maybe it has not trained on animated cats. If that is the case, then the data is novel. Not for us, because for us, we know it's a cat. It's fairly straightforward, but a network has not seen this animated data during training. In such cases, X in this case is going to be novel. So, you want your network, again, you've spent a huge amount of resources in training it. You want your network to still be able to classify it correctly with hopefully a good confidence measure. In this case, again, a toy example, but it basically classifies it correctly as a cat, but with a confidence of 53%, which is about a 36% downgrade from what we had from the previous slide, which was 89%. So our goal is to make sure that there's a robust prediction that is happening. And by robust, I mean two things. One, it's correctly predicted and it's confidently predicted. There isn't as much change from the not novel data in terms of confidence and prediction. So to achieve this robustness at inference, so we need the following things. So information provided by novel data as a function of training distribution. And this is not easy. I'll talk about why that is the case. So methodology to extract information from novel data and techniques that utilize the information from novel data. So what are we saying? We are saying that once you have some novel data at inference, we want to still be able to classify it correctly. And to do that, essentially, we want to extract some kind of different features, because network already extracts features, like amazing features. But if it is novel, we cannot always trust these features that it has extracted. So we want to take a good set of features and be able to classify it correctly based on those sets of features. So what we want is a set of features that are information rich and provided by novel data as a function of training distribution. Now, I started this slide by saying that this is not easy, because let's think of what we mean by training distribution and use the concept of manifolds. So what are manifolds? Manifolds are compact topological spaces that allow exact mathematical representations. So this is like a very simple definition of what a manifold is. Given a network, take a single hidden layer. If you take all, I don't know, if it has trained using 1 million images, if you project 1 million images in one hidden layer representation, it's going to form this kind of a smooth function, or hopefully a well-established, well-trained neural network is going to form this kind of a smooth function. That is what we would call a manifold, because in a very high dimensional space, there is a smooth function, a mathematical function, hopefully, that we'll be able to define that particular manifold. So this is like a toy example of what a simple manifold is looks like. So this is a visualization that is generated using functions, essentially, and thousands of generated data points. This on the right-hand side is, we use isomap, which is a dimensionality reduction technique. So given a large manifold in some high dimensional space, we can bring it down to like 3-dimensional space. And what you see here on the right-hand side is this kind of a smooth function. So essentially, these are manifolds that exist. Now, let's think about, from a neural network perspective, what we need to generate this manifold. Well, by definition, we need some function which is not available in neural networks, right? We don't have a mathematical representation of a hidden layer. It's basically just a simple set of neurons that have been stacked, and we have some output. So the left-hand side is out of the question. We don't have a mathematical representation of that manifold unless we have constrained it, but that's completely different topic. On the right-hand side is also not possible, because the way we generate this is by having about 10,000 different points, passing it through a network, and looking at the activations from that space. That is what you have here. At inference, unfortunately, what we have is a single image and some network that has been trained. So we have a huge neural network which has amazing amount of knowledge, but what we essentially have is just a single point from our novel data that we have. And this is an issue during inference, right? Because at inference, all we think we need is an output from the network. It could be a classification, detection, some generative modeling, anything, but you are expecting an output. rather than thinking about, okay, how was my manifold and how to use my manifold in a different way. At training, of course, you have access to a huge amount of training data, so you would be able to either reconstruct something similar to the mathematical expression or similar to that S-shaped expression that we saw. So we have a number of ways that we can extract information during training, but at inference, that is not available to us. And that's why this is kind of grayed out. So trained network knowledge, of course, we have access to the neural network itself. And the neural network has knowledge, but it's not in a form that is easy for us to understand or to make use. And this is the main challenge for us. We want to get something similar to the right-hand side in the left-hand side. So we want to have the cake essentially, which is the manifold on the right-hand side, and want to use it and basically eat it too on the left-hand side as well, because that is what we want. We want to use this novel data at inference, and that is the main challenge. So why is it possible? Well, let's start by thinking of it from the perspective of information. Whenever we think of information, we always talk about Shannon entropy, Shannon information, which is we pass a model or an image through, we get some predictions, and we get the confidence of those predictions. We just multiply the prior with those confidence, and whatever the number of bits there is essentially what we think of as information, which is valid, completely valid, and it's a very good important setup within the framework, which is information. But there are different kinds of information, and one of those different kinds is this idea of Fisher information. So it's the surprise in a system that observes an event. Usually when we think of information, it's not in the system, it's the output itself, the output of a system. But the change that can happen within the system when it looks at a particular image or a data point is this Fisher information. Essentially, Fisher information can be defined as the variance given some gradients of a likelihood function. There are very good tutorials and there's very good analysis of what Fisher information is. I'm not going to go deep into the idea of what Fisher information is. There are references, of course, in this particular tutorial. You can see those references. But essentially, this is the formula for Fisher information, where theta, which is a statistic of distribution. Of course, if this were a good manifold and there is a mathematical expression for this manifold, then L of theta given X is going to be very straightforward. There's an analytical closed form solution we can derive out of this. But again, not possible, right? We are during inference, nothing is available to us. So it's not as straightforward as just getting this expression and getting a result out of it, but it's still very important because this sentence here is very important. At inference, given a single image from a single class, we can extract information about other classes. It's very hard for me to justify the statement in slide number 26, but at the end of explainability, hopefully we'll look back at this particular slide and it becomes a bit more understandable. Essentially, what we are seeing is that when there is a data point, a single data point at inference, we don't just get information about that data point, we get information about all the classes or all the knowledge that a network has learned, is essentially what we are trying to say here. It becomes very intuitive from an explainability point of view, and that's why I mentioned that we'll talk about more about this particular slide later. But the mathematical aspect of it is essentially that given some kind of this expression, the variance of the gradients of your likelihood function, you can do some kind of a variance decomposition on it and get expectation of something plus variance of something. And again, the derivations of this are elsewhere. We won't go deep into the mathematics of the Fisher information itself, but essentially what you will see is that the information is contained in the gradients with respect to the sample. So this gradients with respect to the sample theta given X, so U of theta is the gradient of the likelihood function. These gradients of the sample itself and the class associated with it have a huge amount of information that exists. And if we had a lot of samples, of course, we can recreate this manifold. But even with a single image, we have a single data point, we have access to some local information. To motivate that, GradCam is a very famous explainability technique for images. So given this kind of a cat dog image from ImageNet, if you pass it through a network and you ask the question about why dog, you have this here on the left-hand side. We'll go in detail about GradCam itself. But given this single image, we can extract knowledge about the word dog, about the class dog, and be able to give this output here. It's called an explanation, but essentially it's the saliency map. It's a heat map that shows you that these are the features, these are the reasons why the image has been labeled as a dog. So what do we have here? We have access to just this one image, which is X, a trained neural network. And what it is giving us using gradients. So this method itself uses gradients, and that's why I'm bringing it at this particular point. But using gradients, it gives us local information around this particular image, around this particular data point, in order to highlight these regions within the image itself. So gradients essentially draw this information from the underlying distribution as learned by the network weights. So network weights have knowledge, have a huge amount of knowledge, and we are utilizing the gradients in order to draw out this particular knowledge. You can think of it as some kind of a prompt. Even though there's no LLM prompt over here, your gradients are, you're using them as prompts in order to derive certain knowledge from the network itself. And that is essentially what you have here on the left-hand side. We'll bring this back again in part 2. Right now, what I am saying is, or I'm trying to motivate the fact that gradients have the information that is required, and it's available at inference as well. So this is just what we discussed, which is gradients have this access to this local information. They provide local information around the vicinity of a particular data point X, even if X is normal. And the reason that you have information around X is because wherever it is, right? Before we saw that it was a blue point outside of the manifold. It projects onto the manifold, essentially. If it projects onto the manifold, now it could be a wrong projection, and that is perfectly fine. We don't care about the type of information, if it's good or bad information. We just want to make sure that there is information that is available to us. And at this point, that is very important to us, the fact that there is information. And we get around the gradients, we get some information around the vicinity of the data, even if the data itself is novel. The next important reason or property of gradient that we'll be using is the idea that we have already used in training. So the best way to train a neural network is by using gradient descent or any algorithm that uses gradients. Now, the reason you can do that is because gradients provide this kind of a direction. It tells you where within the manifold or within the optimization framework you need to move your weights in order to have a good result. So essentially, there are 3 paths available. Again, this is a toy example, but there are 3 paths available. Gradients tell you which is the better path. Is it path 1, path 2, or path 3? And this is always used. This concept, this idea is used quite a bit to try to understand to understand the optimization framework and to use it during training itself. Now, we will not be training the network, which is at inference, you're not going to be updating any weights, but we'll use this principle, the fact that gradients provide some kind of a direction attribute that we will use. And this direction attribute is directly correlated with information, some information about the underlying statistic or the underlying manifold in this particular case. So again, everything that we have looked in this part is just setting up to what we will discuss later during the application process, because we'll be doing something like this. Currently, we have this only. We have at inference, we have a network that has been trained, but we know nothing else about it. We don't have access to a manifold, nothing else. We have huge amount of weights that exist within the network. And we have this kind of a novel data that exists somewhere outside of the manifold. We want to make sure that this manifold becomes as bright as possible. Instead of having this, it's all grayed out, we want to make sure that it is as colorful as possible, or in other words, we have access to this manifold. And the way we'll do it is by 2 things. One is this kind of a counterfactual or contrastive representations using gradients, where we'll create this kind of a different manifold, a similar manifold, but we'll use the fact that local information is available, and we'll create this kind of a counterfactual manifold around that point in order to understand the manifold. Because again, our manifold is not available to us, but if we create our own counterfactual manifold, it may be something that we can use. And on the right-hand side, we'll traverse through this representation using gradients. It's possible, again, because of the fact that we have access to different paths. We won't know which is a good path, but that's fine for us. For now, all we want, again, it could be a completely wrong traversal, but it's giving us some information about the manifold itself. That is the goal we will be going through in this particular tutorial. The part 2 and 3, which is explainability and uncertainty, will be the left-hand side, while the right-hand side will be the last part that exists. All right, with that, we come to part number 2, which is, yes. Activations. I just mean the activations in that particular point. Yeah. So we now come to explainability, which is part number 2. We'll describe a few things here. We'll go back to the GradCam, gradient-based explanation, specifically GradCam, and we'll take a deeper look into what GradCam is, and then discuss the counterfactual and contrast cam out of this methodologies that are there, essentially. So this was actually a paper that we had written about a couple of years back, and trying to understand it in terms of different paradigms of explanations. So let's say we bring back the cat dog image. If I pass this through a VGG16 architecture, I am going to get the output as a bull mastiff. I think it's like class 243 or something like that. What visual explanations are basically that a set of rationale used to understand the reasons behind a decision. This is like the ideal goal of what an explanation is. Given a certain image, I will pass it through the network. I'm going to get an output, but I want to know why this particular output has existed, why this particular output was given by my network. And to do that, we have all these ideas of explanations and stuff like that. So we can ask different kinds of questions, right? So we can ask, let's say, why bull mastiff? Why the network said it's a bull mastiff? And we get this kind of an output. We can ask different kind of questions. What if this bull mastiff was not in the image? And we'll get this, then the network says that, okay, I'm not going to use this image at all for making a prediction. I'm going to use this cat image, and I'm going to give a certain different prediction, but I'm going to use these features, essentially, is what this counterfactual explanation is saying. And we call this counterfactual because of the presence of what if. There's a what if in your question, then that means it is a counterfactual. A different kind is a contrastive thing. So why P rather than Q is contrastive question. So, okay, why did you say that it's a bull mastiff? I would have suggested that it is a boxer, is the question that we are trying to answer on the right-hand side. And it's showing this bottom part here. As you can see, there's only slight overlap. It's saying that the jowls are heavier for this particular dog, and hence it's being classified as something else. Now, I want to be very clear what we are showing here. A network has learned that it is a bull mastiff, but it also knows that it is not a boxer. And if I were to go back for a couple of slides and tell you that, a network at inference, it's not just the image of the bull mastiff that it knows. You can actually extract about other things as well. This is what I mean. I have a couple of other slides later on that basically discuss this, but you have access to a huge amount of knowledge within the neural network that you can extract during inference, because we have not trained that this is not a not something rather than this. We have not trained what if. It's just explanations that we can get on the fly during inference. We'll be able to get these kind of explanations, and that information is stored within the neural network. So going back to the idea of what explanations are, we want some kind of context and relevance from the explanations themselves. Let's say I'm given this image of a spoonbill here. A kid is going to ask a very simple question: why spoonbill? Because the kid does not know. The kid is trying to learn why spoonbill, and the answer could be some kind of a pink and round body, straight beak, and this is sufficient for a kid to actually learn about what spoonbills are. But let's say there is an expert here, an ornithologist, who's asking the question, who's not just asking the question to understand why, but rather is testing the network, is assessing what a network is doing, and asking why spoonbill rather than the flamingo. A simple answer here is the fact that flamingos usually have this S-shaped neck, which is not there in this particular spoonbill. Hence, a lack of S-shaped neck is what a network says. Now, the ornithologist can be happy with it, or ornithologist can say that, okay, yes, neck is a point of difference, but there's also another difference, which is the legs between a spoonbill and flamingo. Maybe a network has not learned about this particular definition. Or it could be some kind of existential question from a fox's point of view: why spoonbill rather than a fox? And everything is different. The neck, beak, body, legs are all basically different, which will make the fox happy that they're basically not a spoonbill. This essentially garners trust within the framework. So it's very important from the perspective of explanations that they hit all these points. It's not just going to be explaining your decisions. It has to you have to be able to assess the network. You have to be able to gain or garner trust in the network. And explainability, each and every point of explainability helps us do this. Again, all these are actual images from networks that we have derived. It's not these are not toy examples that we have. We'll discuss about how we get this in a little bit. So going back to the idea of what gradient explanations are, gradients are something that we have utilized completely during training, right? And the reason we do it is we want to make changes within the network in order to get a good explanations. Now, instead of just making changes within the network, if I backpropagate to the very beginning of the neural network and show you what the gradients look like, this is how the vanilla gradients are going to look like. There's going to be small changes in terms of deconvolution and guided backpropagation. Specifically, you put a ReLU architecture on or ReLU function on the gradients as well in order to get this kind of a guided backpropagation. But essentially, you'll be able to process the gradients and be able to get all these three different explanation looking images. You have that of a cat, and this also a cat, but multiple other things. There's a lot of literature that has gone into saying why gradients are good explanation. There's also a lot of literature that has gone into saying why gradients are a bad explanation. All they're doing is just reconstructing the image. And is that something that we want out of an explanation? Maybe not, right? We want to know why a network essentially said that it is a cat rather than just recreating the cat that already exists, that we know already exists within the image. So gradients, they are a good source of explanations, but rather than just use gradients as the source of information or as explanation, we would rather use them as a function within a framework in order to make explanation. And that is something that was done in GradCam. Gradient class activation map is the full form of GradCam, essentially. GradCam uses the gradient information flowing into the last convolution layer of a network to assign importance values. So again, we are moving away from defining what an explanation is. Instead of saying that all human beings, this is why they predicted it was a cat or a dog. It's basically the saliency maps. It's the important features within an image that leads to a particular decision is what explanations are. And GradCam gives us a very good answer to this. So given a huge neural network, you have a lot of convolution layers or some kind of layers within the network that gives you an output. And you take the outputs from that convolution layers, mix and match using fully connected layers to get the output. So as soon as you put fully connected layers, you lose any localization information. So you want to make sure that you get your outputs or features from the last convolution layer. And if you use these gradients within the framework, you'll be able to get this map over here. So let me go through this step by step, what exactly we are doing within GradCam, because it's very important later on as well. So within the GradCam framework, I'm taking again, everything we take here is a trained network. So I'm taking a trained network, in this case, let's say a VGG16 architecture. I take the image of the cat dog that we have seen from before. I pass it through the network and I get an output as well. I get whatever output that the network is giving us. Now I take the logit of the prediction and I backpropagate it. The logit of the prediction itself is going to be backpropagated through the network. So each layer, chain rule, you're using backpropagation to go back until the last convolution layer that you have at this particular point. So at the last convolution layer, what we are going to do is just global average pool for every different feature map that we have. Each of these feature maps need to have one number, which is going to be our alpha K. C basically is the number of channels. In this particular case, how many is there? That's about 6 different maps. So each of these maps will have a certain value associated with them, which is the weight matrix that is based on gradients. So instead of using gradients directly as the features of explanation, what we'll be using is they'll be used as weights within the explanation, because what happens to this alpha KC is that it multiplies the channels themselves. So at this particular point, alpha kc, which is a function of our gradients, multiplies the channel, and you put an ReLU2 through them, and you get this particular output. So essentially, you have activations, which is the projections, which are very important for getting our prediction. And once you have that, you weigh these activations based on gradients in order to get this kind of output. So essentially, you're using this information as a weighing function, information within gradients as a weighing function in order to get this kind of output here, which again is extracting the local information from the activations to get this output. This is one way of thinking about what GradCam is. The main procedure, of course, is that we backpropagate the logit, which is the output from a network YC, back through the entire network. Now, GradCam is very famous, the reason being that it can be used for any kind of an application. Any network that has gradients that can be used, that can use gradients essentially within the framework, can use GradCam in order to get some outputs. Image classification, captioning, BQA, and any application that exists, we can use GradCam in order to get outputs. Now, let's go back a little bit and think about what GradCam was giving us. So if I have my image as a bull mastiff, I can ask the question of why bull mastiff and get these explanations here. So we can call this as an observed correlation because it's answering why P kind of a question, right? But this is not all we want. We want different stakeholders to have different explanations. We want an ornithologist to get a different explanation than a kid. That's what we saw. So essentially, we want to have different kinds of explanations based on some questions, which are this YP, what if, which is a counterfactual question, and why bull mastiff rather than a boxer, which is like a contrastive question that exists. So how do we take existing methodologies like GradCam, say, and provide these kind of explanations? So let's start with a counterfactual explanation. So the same authors who first introduced GradCam, in the same paper, they had this other thing as well. They hadn't highlighted it as much, but one of the way they did it was instead of backpropagating the logit, you backpropagate the negative of the logit within the same GradCam framework. You get alpha kc, you multiply it with the weights. So essentially, you're weighing the information in the negative of the logit. You're using the gradient information and multiplying it with the channels. So in other words, the gradients carry this negative information, and they do it in a way that it's now the network thinks that I just need to subtract all the features that was used to make the dog classification. So essentially, all the features within the dog are kind of negated, are not used to make the classification, because again, you have a ReLU over here, which is going to take out all the unimportant or the negative information that exists. And what is left is this particular cat image. In other words, what I want to highlight here is the fact that the global average pool, the negative of gradients, is what is used in order to get this kind of information. So we have manipulated our gradients in order to get different information than what a network was initially using in order to make the initial decision. Now, how do we get like a contrastive explanation that we showed before? Well, instead of backpropagating a simple logit, we can backpropagate a loss function between the prediction and some kind of a contrast class. In this case, it could be bull mastiff and a boxer. You can take a loss function between these two things and backpropagate your this particular loss, in which case you're going to get a contrastive explanation. Again, the explanation methodology framework is the same. It's still GradCam. It's just what kind of backpropagation you're using, what kind of gradients we are using, is giving us these kind of different information. And I think that is very important, because gradients are the features that we are going to be using, or at least we are advocating to use at inference. What we are showing here is that based on 3 different processing that we can do at the inference stage, we can get 3 completely separate explanations that can be used for different stakeholders. So let's look at this from a more from multiple images to see what exactly happens here. So in this particular case, we have about 4 images on column 1. We have the GradCam explanations in column 2, and in columns 4 and 6, we have contrastive explanations, and we have the questions also here. I'm not sure how easy it is to see what the questions are, but based on different questions, ideally your network is supposed to give you different answers. So let's go through them one by one to see what they look like. So let's try to classify them. Let's say that there are some explanations which are very human interpretable. So given an input image, GradCam image is giving us a very good idea or reason why it's a spoonbill. Given this cat dog image, it's giving us a very good idea of why it's a dog. Same thing with the no left sign as well, right? It's showing us the fact that there is this kind of a bar across the image, which is the reason why it is a no left image. And same thing here with that of a convertible. It is a Bugatti convertible because of the shape of this particular car. Now, these are very nice results to have, but sometimes it might not be enough to understand whether a network has actually learned what human beings think should be the explanations. And that is where the contrastive explanations can come in. So for spoonbills, this is something that we saw. Usually spoonbills and flamingos have this as shaped neck, and you have the neck that is being highlighted in this particular case to show that why it might not be a flamingo and why it is a spoonbill. Look at the one at the bottom here. So you're asking the question of why is it a Bugatti convertible rather than a Bugatti coupe? And the contrastive explanation is highlighting the top. The fact that the top is down for this convertible is a very good reason why it is a convertible and not a coupe. So this is the reason why it would be a convertible rather than a coupe. And that is what the contrastive explanation is showing us. And this, looking at this image, it garners trust essentially. Okay, a network not only knows that it's a convertible, it can also tell us why it's a convertible rather than something else. It can show us these kind of fine-grained differences that exist between the classes it has learned and within the data, so as to, it helps us garner trust essentially in what the network has learned or not learned. And all of them are human interpretable. So I can stand here and tell you why it is the case without blinking essentially. I don't need to think about why these are the answers in this particular case. Some of them are same as GradCam, which is perfectly fine. Like if you look at this question, why bull mastiff rather than a blue jay? Perfect. Yes, you don't need to know any other solution here. The fact that this face is what it is why it's a dog and it's not a simple bird. So it's perfectly reasonable to say that it's the same as GradCam. And the same thing here as well. Why is it not an SUV? Well, everything about a convertible is different than an SUV. And that's the reason that it is different. It's the same thing, right? So the information that it's showing at this particular point is good, is what we are expecting. But then there are some cases where it is not, well, I don't want to say not human interpretable, but it's not very obvious to start off with why this is the case. Now, if you were to ask me the question, why no left rather than stop sign, I would have said personally that the fact that there's no S, T, O, and P within this no left image is the reason why it's a no left image rather than that of a stop sign. But what a network is showing you is this, this kind of highlight in the bottom left corner of the image that exists over here. And it's not very straightforward when you first look at it and think, okay, why this is the case. But let me show you the data set that was used in order to derive that particular image. This data set has 14 different traffic signs. Again, this is the German data set plus the Cure TSR data set that we showed earlier. There's like 14 different traffic signs, and this is how they look like. One thing I want to talk about here is the fact that the stop sign is the only one with this kind of a, how many is this? This octagonal shape. This is the only one with this particular shape. So in other words, you see the bottom left corner here, you don't find this kind of a corner in any other class. The fact that a network is not able to detect this edge, this bottom left edge, is sufficient. It doesn't need anything else in order to say that it's not a stop sign. We might say that STOP is very important, but not a network. A network is as lazy as it can get. It's like your water running down the mountain. It's going to take the shortest, the simplest, the best path in order to get your solution, and that is what it's using. If I go back to this particular image here, it's only looking at the bottom left corner of this particular image. Now, depending on what you want out of a network, you might either be impressed or not impressed with this particular statement. if you want to align your decision making with that of humans, this is not good. You don't want a simple bottom left edge not to have it, because what if I take my photograph slightly to the right hand side and it's occluded? You won't have this bottom left corner in that case. You want to have STOP as the reason why it is not a stop sign. But if your goal is to have a very accurate result, get the best possible result, then this is maybe something you would want. But either way, without making judgment on whether it's good or not, gradients are giving us this information. It's telling us how a network has made this kind of a decision by highlighting certain regions within an image. And by changing this, the loss function or the negative of gradient, we get a different kind of a result and information. Going back to the statement that we made earlier, at inference, given a single image from a single class, we can extract information about other classes, right? So this was the image that we started with, and hopefully it will become this statement, which is very intuitive, is going to become clearer with these couple of slides. So let's say I have a spoonbill. I have a network F that passes through the spoonbill passes through the network. And let's say there is a discrete set of features that it has learned: beak, neck, legs, feathers, water, grass, teeth. And in order to say that and all of these are essentially my tau, which is the entire framework that exists. So given this image, this network, the let's say gradcam or some kind of a function is highlighting these four things in order to say why it is a spoonbill. Now, a contrastive explanation, if you ask this kind of a why spoonbill rather than flamingo, it removes the beak, neck, and feathers, only keeps the neck. In other words, given a spoonbill and a trained network, its neck is different than that of a spoonbill. This we know. So this is the reason I'm talking about this is that it's a very powerful result with the right way of gradient extraction. So we can infer about other classes based on just this single image of a spoonbill. We have never seen, at least in inference, we have never seen a flamingo. And yet, based on a spoonbill's image, we can get to know something about a flamingo. And this is what we were discussing earlier. The information that exists within the network and a single image at inference, we can use it to get all other information about other classes as well. And this information is essentially encoded within the gradients. We have to manipulate this gradients, of course. We have to take a loss function, or we have to take the negative, we have to take the logit itself. But either way, we can manipulate the gradients and the loss function in order to get a good representation out of it. And that essentially is the main takeaway from the explainability framework. Of course, that the features exist, or the information exists within the network, and based on these contrastive counterfactual explanations, we can extract them. So that brings us to the end of part 2. I think I'm good. We have about 4 more minutes until the break. So the next part is going to be about uncertainty. So maybe what I can do is I'll very briefly talk about the definition of what uncertainty is before we can leave for a break. Very simply put, uncertainty is a model knowing that it does not know. So there's 300,000 definitions of what uncertainty is. We're going to be talking about this very simple definition of what uncertainty, which is that a model does not know what it knows. So look at this image here, for instance. I got this out of the internet. So given this kind of a sinusoid waveform, let's say it only exists between -0.5 and 0.5, what you see is, you can clearly see that it's a sinusoid. But what a network sees between -0.5 and 0.5, it's able to reconstruct quite easily because you have a lot of data at these points. But as soon as it moves away from that domain, it has no idea what needs to happen. If you were to ask me, given -0.5 to 0.5, I would probably put this up to infinity. It's a sinusoid. It's a sine wave, essentially, that keeps on going to infinity on one side, minus infinity on the other. But maybe in reconstruction is not the case. So what a network does is essentially it tries to go up, but since it has no data on the other side, it keeps on going down. So when there is no data, we essentially have uncertainty, and this spread here gives us that particular uncertainty. And this is a problem for us because during inference, if there is novel data, there is nothing available to us on the left and right hand side. So you should not be able to trust your results at all on the left and right hand side. And we want to make sure that at Inference we have some kind of features that we'll be using in order to get these outputs. So that would be a very simple definition of uncertainty. Maybe we can stop at this particular point and take a break and maybe see each other at around 10:30, I would say. We'll have a break for about 30 minutes. I'll recharge my vocal cords as well, and hopefully I'll be back with more energy, essentially. Oh, thank you. We'll be back again, Savina. Yes. Uh-huh. Yes. Yes. Yes, we did. Yes. Yes, I think so. Explanations I talked about was just very simple visual explanations. Yeah. So there's a new thing called concept vectors. Concept vectors are essentially, instead of looking at them from indistinguishable features, we look at them as concepts. So there is a data set of, let's say, birds data set, and there are actual, and I think the name of the data set is birds, and you have access to some features of the birds, and instead of highlighting in the image, it highlights those features. So it is there, and I don't think I talk about concept vectors, but essentially that is thing there. Yeah. Mhm. It could be used for vision language models as well. Mhm. Yes. 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 Oh, okay. Okay. I see what you mean. Yeah. 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 Yeah, I think so. But since you mentioned, yeah. Yeah, 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 it works. It works quite well. So the same thing, if you backpropagate the gradient. So instead of, again, there's different stakeholders, right? If we are talking about lay people who are using it, I think an LLM would be perfect for utilizing this. You directly ask them what the questions are and you get the answers. But then you don't know when it's hallucinating. And that is when you have to go into the network to try to dissect and try to understand what is happening. And the question then becomes, can we as engineers essentially do the same thing without using the language capability? Because again, the LLM itself, you think about click model, there's two separate modules that are going. Any foundation model, for instance, right? It's just a transformer with self-supervised learning. So at the end of the day, during inference, we don't care about how the training has happened, as long as there's some kind of decision and there's some kind of gradients to thing. Explainability, exactly. So you'll get that output was the thing. But yes, we have used this in language VQA question answering models as well, where it's able to give us what the answers are. Yes, exactly, exactly, exactly. Yes, because again, we don't want to confuse the two modules separately, and just to see how we can clamp down on that hallucinations is actually what we are doing. Mhm. Yeah, yeah, yes. Spoonbill. Yeah. No, there's no flamingo in the setup itself. Yeah. So the class, let me just go back to this one. So you back propagate the wrong class. Q is flamingo. Yeah. Yes, yes. Oh, yes, yes, yes. That's what you meant. Yeah. Yeah, it has to be there. Yes, it has to be there. I'll talk about later. Yes. Yeah. Yeah. Mhm. Yeah. But again, class is not required. I'll talk about in latest, actually during uncertainty, the third part. Different, yeah. No, 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 no. Yeah. Exactly, exactly. Again, in end of uncertainty, there's a way you can change the predictions as well based on this information. So you can have a small separate module, a very simple three-layer architecture that you can use in order to get a better prediction. You can change the prediction there. Yeah, yeah, yeah. Something, yeah, yeah. Yeah, actually, yes. Yeah, of course, no worries. Fine. Yeah. Mhm. No, you don't need Flamingo. You have trained modules, so it has trained on Flamingos. But yes, yes, it has trained on Flamingos. Yeah, contrasted. This one. So you backpropagate. So this network was BGG16, trained using cross entropy laws. So you use cross entropy between whatever the prediction is. In this case, it is a spoonbill and whatever contrast class you want, which is a flamingo. So essentially, it's like you're during training. If again, this is the wrong class. This is truly a flamingo, or in this case, it's a dog. You're backpropagating the wrong class. Yes, J is cross entropy. Yes. No, no. You can use any network that has been trained in any way, and you can backpropagate a loss function. In most of my experiments, I've found cross entropy is the best thing that gives you the output. But essentially, if you backpropagate using cross entropy loss, even though it's the wrong class, it tells you what needs to change within my knowledge, within the network's knowledge, to incorporate the fact that this is incorrect, essentially. Yeah. Yes, exactly. Yes. Not correct. So it's a prediction and the contrast. So it may be correct, it may be incorrect, it doesn't matter. We are not, at this point, we are not interested in whether about the correctness of the prediction, rather that there is a prediction which has been made, which has been, and contrast is whichever you want. At this point, again, it's all like existing classes, but during uncertainty, we'll talk about when we don't have access to classes, but in generative model like autoencoders or even in classification modules, when you don't know which is the best to define, what else can we do for Q is what we discuss. Yeah. 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 So there's two ways of thinking about it, right? GradCam is showing you how good a network is rather than showing you what the actual explanation is. So you should never look at GradCam or any gradient-based explanations and think that this is this is the explanation for a certain class. So if in a medical setting, for instance, it's really not showing you an explanation. It's showing you why a network did what it did. Any gradient-based thing is just reconstructing the image. So essentially, you're weighing the reconstruction to say these are the main features that used it. I don't know if I have the slides here, but a causal explanation is the probability of given class Y given certain features. But this explanation is opposite. You're given your class and you're asking what the features are, which is not ideal, which is not good. So, but in terms of trying to understand the network, I think GradCam is probably the most ubiquitous and best used algorithm and should be your go-to to start off with, at least, is my opinion. Exactly. Exactly. Yes. Yeah, it's not an explanation. It's not an explanation by itself. It's what a network is doing rather than this is the reason. So it's I don't know if I have those particular slides, but in this particular paper here, we actually discussed that the difference between what a causal explanation is. That's why I think when we first wrote the paper, we had it as observed causal explanations, but there was a lot of problems with it. So during the back and forth with the journal, it was like, okay, these are correlations rather than causal explanations. So that is the main difference, that the probability of y given x versus x given y, or s of x, which is the subset. Yeah, yeah, of course. Mm-hmm. Sorry. Yeah, it's Python code, and there's a lot of papers. I'm sure this is from the same university I'm in as well, grad camp, Georgia Tech. So uh, everybody uses it. It's a very ubiquitous algorithm. Yeah. Do you mean yes? So let me go there. So if you go to this particular website, if you scroll down somewhere near the middle, you have 5 different parts where if you click that, you'll be able to see each of the 5 slides. That should give you access. Yes, that should give you access. Let me actually make sure. It's correct, right? So if you go to the bottom, below tutorial description, below tutorial outline, there's 5 different parts with links associated with it. So each of these links gives you the slides for those particular parts. Oh, then maybe on the right-hand side, I should have that rather than a screenshot of this one for next one. If anybody online, I hope you can hear me. If you have any questions, just put it in either the chat or Q&A. Currently, there's no questions. It's hard to see here. Sorry? No, I don't think so. And intervenability is more related to the fact that you will have, you can intervene on top of data. Usually in causality, this is what we do. We see what the result is, we intervene, we see again, and we keep on going back and forth in order to get this thing. But I don't think I'm aware of what algorithmic recourse is. Okay, 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 sure. Oh, I see what you mean. Okay. Yeah, exactly. Yes, you can't. Yes. Yeah. Okay. It's more general. I just use those 3 because those are like the 3 paradigms of reasoning. Like if you go through the reasoning from a philosophical perspective, there's like deductive, inductive, abductive. And generally, I mean, I don't talk about this too much, but essentially, a neural network is an inductive framework. It has seen our inputs, and it gives you an output based on the fact that it has seen. But we can convert that into an abductive framework by asking 3 separate questions. And the reason we chose these 3 because it forms a complete explanation. It Every single feature is going to be highlighted if you ask all possible these kind of 3 questions. And of course, why spoonbill rather than flamingo was one question, right? I could have asked why spoonbill rather than blue jay, why spoonbill rather than bull mastiff. So based on all existing things, there is thing. And if you start looking at the output not as the names but as one hot vectors, Why spoonbill rather than flamingos? Like 0, 0, 1, all zeros. What if I had 1, 0, 1, all zeros? It's still, I mean, it doesn't make sense from a question perspective, but it's still something. So you can have 2 to the power of n, which n is the class's number of questions. So it's like 2 power 1,000 for ImageNet. So there's a huge amount of questions just based on this thing. So 3 paradigms, but 2 power n number of questions that can be asked essentially. Okay, I want to make sure this is okay. Yeah. Or the joules, the joules. It's showing the fact that joules don't exist within this image. So still yes. Yes, please. Yes. 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 So I think the easier, that's why spoonbill is easier. The fact that S shape doesn't exist is the reason. Technically, what is happening is these are the things that must change within the data in order to get boxer image or to get the spoonbill image. That's the technical way of thinking about it. Desired features it needs to show. So it doesn't exist or it needs to show. Yes, exactly. Yes. Yes, that's the PQ. Yeah. Hi. Oh, hi. Oh, we did? Okay. Oh, okay. Okay. Mhm. Okay. Uh-huh. Yeah. 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 Okay. Yeah. Yes. Yeah, I agree. Yeah, okay. Okay. Oh, really? Okay. Interventions. There's a huge change that's happening. Yeah. Yeah. Okay. Mhm. Okay. 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 Uh, oh, again, this is more of an opinion. interpretability is like, so cause there's this things called Russian dolls where if you just open one, other dolls, right? So I think the overall thing is causality. Within that there's interpretability, and within that there's explainability. So I think everything which is GradCam is something that we can see, that we can understand. So from that perspective, it is explainability. But I think you will be very interested in the third part that I will talk about, which is intervenability, which is exactly this. Like insertion deletion metrics, a huge problem because they introduce these large.
Right. So you agree?
Yeah, I completely agree. I 100% agree. But I don't know if in painting is the idea, is the right
So
answer.
one of the reviewers very tough on that. I want to say that I'm trying to convince him that
Yeah.
we try to say that we could use it.
Yeah, but it's not.
But it's logically it doesn't make sense.
I agree. Yeah.
Anyway, so I think I just.
Okay. Yeah. In part 3, I think, so not part 3, part 5, the intervenability, I talk about this exact thing about how insertion deletion is a problem. And maybe, the way we evaluate our explanations is incorrect. At the end of the day, by doing this kind of any kind of intervention, we are not explaining it. We are just reducing the uncertainty.
Right.
Which is an issue because, again, I think with someone else I was talking about how explanations is not an actual explanation,
right.
Which is it's just a saliency map. It's not this thing, which is good. I mean, it's very important. Yeah, it's a visualization. Yeah, it's very important to do that as well. Like if you just throw another LLM on top and get a certain output, you need to explain the output of that, and that's why we do have this hallucination issues, which we are working on in terms of prompting and stuff. But how do we? So the definition, going back to your question, I think it's still up in the air. Like we have like a philosophical definition, but the engineering definition is not our philosophical definition. That is a huge issue. Like the way we evaluate it is completely incorrect explanation. So there's no way we can have a good and yeah, in painting I think I think I'm more for insertion deletion than I am for in painting, because
right. At least that's the objective metric,
yeah,
right?
yeah, there's an objective metric over there. I can use 20 different algorithms to get 20 different in painting, and everything will give you a different explanation, give a different solution. It's really hard to justify something like in painting.
Maybe we could talk a bit.
Sure. Yeah. Yeah. Okay. Yeah, I love that. Yeah, that's fine. Yeah, my email is somewhere. So yeah.
And also it's pretty close to
Oh, okay. Okay. You're from Carolina? Oh, North Carolina. Oh, okay. North Carolina. No. Does this work like Neurips, where I can take your this thing and I don't know where my phone is actually. I think I kept it there. That's good in Neurips, by the way. They have this kind of thing. I haven't tried. I didn't try before, but nah. Okay, that's fine. Yeah. Yes, please. Yeah.
That's good. Then I'll let you rest up a bit before the next one.
Yeah. Mm-hmm. 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 Exactly. Yeah. Okay. Yeah, yeah, yeah. Yeah,
Sure.
I agree. I think so. In that paper, we have classifications, categorizations into three things like direct, indirect, and targeted explainability. So direct is what you're suggesting, which is basically a human being at the end of it has no knowledge of data, has no knowledge of the
Shouldn't care.
network. Yeah, shouldn't care. Exactly. It's like someone in from an autonomous vehicle perspective, it's a user essentially, or someone from the insurance companies essentially. They don't need to know the engineering details that has gone in, right? But that would be a direct explanation. So in that thing, we have like listed different these are the direct explanations. Indirect explanation is for more for engineers, while targeted explanation is the contrastive and counterfactual. It's kind of in between. Like you don't need to know the exact details of the training, you don't need to know the definition of weights, but you need to know the fact that there is a fine-grained difference between spoonbill and flamingo to say that, the assist thing from the ornithologist, the fact that the legs are different but it was not showing. So that's more of an assessment kind of thing. So you're absolutely right, everything is more from that assessment, but direct explanations also exist, and we have that in the paper where we have listed it in the table. No, it was a different one. uh, no, 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 it's fine. Uh, this paper down here, explanatory paradigms in neural networks. Yeah. Sorry. Yeah, perfect. Yeah, yeah, yeah. It's Mhm. Yeah, yeah, yeah. It's still hard. Yeah, yeah, yeah. Sure. Yeah. Yes. So it also depends on the kind of prompts that we are discussing, right? Like during uncertainty, I'll talk about instead of backpropagating. So if you're backpropagating a spoonbill, then that essentially means it's a one hot vector, 0, 0, 1, all zeros somewhere. So take the word spoonbill out of it. Why are we backpropagating this one hot vector? What if I say we backpropagate 1, 0, 1, all zeros, or 1, 1, 1, all zeros? So it just gives you so much different kind of information, and what can we do with that is essentially. So again, this is more targeted explanation kind of a thing. From a direct point of view, I think it's really hard to justify. Um, um, I shouldn't say that. You obviously have to justify and give explanations to the consumers, right? But from an engineering perspective, I think from an engineering perspective, for the people who are doing the models, right, they have to know these things. They have to know the networks, the classes, the one hot vectors to get this thing. But yeah, in the paper we have those things. We have listed all the direct explanations, but I don't have a very like a big opinion on, oh, this is better or that is better. No, no, no. But concept vectors is something that you should definitely look at, I would say. So this you have, you need to make this assessment that, okay, this is joules, this is phase, and all these kind of things. Concept vectors start with those definitions. Yeah, it has. So ideally, during your training stage itself, you must have these kind of, which you do, right? Because you have an entire scene, let's say, and you have 3D bounding boxes for cars, 3D bounding boxes for pedestrians. Exactly. Exactly. Everything. So you have access to all these things. So your data set comes with these concept vectors. So can we? So what you would have to do is not highlight the lanes, but rather if there's a word lanes in your concept, you just have to tick mark that or highlight those kind of things. And that's the only thing that comes to my mind in terms of what is the best direct explanation for autonomous vehicle setting. But again, I don't have a very strong opinion as to way one is better or worse. Right. Right. Yeah. 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 On the top, this thing is the QR code for this particular paper. That is. Okay. Yeah. Right. I think with that we can restart the session. I'll just make sure that I'm still sharing and right. Perfect. So we'll start off with uncertainty. We just discussed very quickly what uncertainty is. And simply put, it's the fact that a model knows that it does not know. And that's a very, very broad classification, as I mentioned. And narrowing down the scope quite a bit, we can say that the novel data, at least the goal, the objective of the tutorial is about novel data. So when data is not present in a certain region of operation, a network should know that it does not know. A network should know that at these regions, it should not trust its own decision. Essentially, that is how we are discussing uncertainty, which again is not the true definition, but it's sufficient from our perspective for now. And the easiest and possibly the best way of getting uncertainty is by ensembles. Train 50 different networks and see what the output is from a single cat image. In all cases, you'll see that there is a slight difference that happens. There's many names for this. Uncertainty is one. Underspecification. There's a paper, I think, 2 years back from Google where they discussed this phenomenon called a related phenomenon called it like underspecification. But essentially, when you take a neural network and have different seeds and you train it in different ways, you don't get the exact same output. You get all different outputs. And you either take the entropy or you take the variance across them, and you'll get something called uncertainty of this particular output. That's the easiest and the best way of doing it. But it comes with a natural inherent problem that there are these n different architectures that you need to train. And I'm not sure that is something that can be justified in most cases where it will be used. In fact, at Inference, if we go back to what we had before, we only have access to a single network and single data point. That is what we started with as assumptions or as constraints that we put on ourselves. This is how we started with. So we don't have access to these kind of multiple networks that are available. So there are different methodologies that try to overcome this. MC dropout is a very famous methodology where instead of having different networks, you take a single network and you randomly, with let's say 20% probability, zero out certain weights. So essentially at and you do this across like 50 different iterations during testing phase. So essentially you're kind of simulating a 50 different architectures and then taking the entropy or the variance to get an output. But in a lot of scenarios, when you actually look at the empirical results, it might not always give you the best possible results. So in either cases, it's really hard to justify having an ensemble based output as your uncertainty. And you try to simulate that using this kind of a single pass uncertainty, where all you're doing is getting this distance from given this kind of a novel data point. You want to get this distance from the manifold that exists, and that is your uncertainty. But again, this has its own set of problems, right? Because as we discussed, we don't have access to the manifold at all. It becomes much easier if you have access to the manifold and you can take a good distance measure, and you can go ham with the type of distance measures you can get. You can have geodesic distances and many other topographical analysis. You can do these topographical analysis in order to get your distances and output. But since we don't have access to the bottom manifold here, this is a very, very different and a difficult problem to start off with. So again, the class and prediction cannot be trusted right now, because if your data is novel, you're in that region of operation where your network has no clue what is happening. It could be an infinite sine wave like we had here, or it could be just a band limited signal that exists only between minus 0.5 and 0.5. And you wouldn't know what the output has to be. You should not trust your network. You should not trust the prediction at this particular point. I think I'm using the words trust and uncertainty interchangeably. That's not exactly accurate. Uncertainty is a component within trust. Trust can be broken down into four things. It's a very esoteric thing, so we won't discuss about it, but you can look at the philosophical definitions of trust, and uncertainty is one component of this entire framework. So, okay, so let's talk about specifically what we are interested in, which is gradients. We started off by talking about how gradients are important for us because they help us get some kind of information. This could be either simple local information, or this could be a more traversal kind of information based on the paths that they are choosing, right? So our goal right now is to now expand that information and talk about how we can use these gradients in order to do uncertainty as well. So gradients will be like the threads that connect all these paths together, at least until this point. In the next part, which is intervenability, we'll not only correct based on gradients, we'll also correct based on explanations, uncertainty, and intervenability. So bear with me in this particular part where it might seem it's completely disconnected with what we were discussing before, and the only connection right now is the gradient part. But we'll try tie it back together all at the very end. So let's talk about specifically two techniques of using gradients in order to calculate this idea of uncertainty, or calculate this idea of distance. The first one will be some kind of gradient constraints during training, and the next one is going to be backpropagating confounding labels for out of distribution detection. So we'll talk about it from an application perspective. The first one will be anomaly detection, while the next one is going to be out of distribution detection, noise detection, corruption detection, and adversarial image detection. All of these things can be done using gradients. So let's start with the first one, which is anomaly detection framework. So this was back in ECCV 2020. First off, what is an anomaly? It's very simple. There's some patterns in data that don't conform to what we had learned. So in this case, the heartbeat, essentially, we have PQRST. You see that the problem here is in S, essentially, that it's not what you wanted. So this is an anomaly. This does not always happen. For the majority of our lives, PQRST is done in a very nice, simple, good fashion. But as soon as there is a problem, that's life-threatening. So anomalies are very, very important in this particular setting. Same thing with the bottom one here as well. You have everybody walking in a certain direction, while there is this one person who's biking in the wrong direction or the opposite direction. So that person is possibly an anomaly in this setting. So a simple definition of anomaly is that there is a stationary process that for the 99.9% of the time, it is going to give a simple definition and going to give a normal process. But there might be some error, and this is critical, that then this error can be critical, like in the PQRST thing. And we want to make sure that we evaluate and get this, what this error is going to be. So normal data, and we get these kind of anomalies. Now, the reason we are discussing these anomalies is that in the context of uncertainty is that if we agree that uncertainty is a simple distance between a manifold, between the stationary process and the data, then it's basically just the fact that if you had a simple threshold here, the fact that this is away from that threshold by a certain amount can be the uncertainty. Again, it's a very simple way of looking at what uncertainty is, but for now, that is what we are going with. That's a narrow view of what uncertainty we will be taking at this particular point. Okay, so how do we actually obtain anomaly? Ideally, since the fact that 99.9% of the time you don't have you always have a process that is going to give you normal processes, you want to constrain those normal processes based on something. This is a particular manifold. You want to make sure that this manifold follows a certain way of working. Like if you have seen variational autoencoders, for instance, they have a constraint. They have a constraint that the hidden layer, the latent representation, has this idea of a Gaussian distribution. So based on this hidden Gaussian distribution in your latent representation, you kind of can make this argument that, okay, this particular data point is away from the Gaussian by more than 95%, then essentially more than 0.95 in its confidence interval, hence it is an anomaly. That is essentially what we always do in terms of anomaly detection, by having this kind of constraints within the manifold, and then statistically detect implausible projections, which is based on confidence intervals. Again, we won't go into details of that, but essentially it's about finding the statistic, and beforehand we'll do some kind of constraint. So There are a number of papers actually that does this very well, in fact, in terms of anomalies, which is given this, let's say, training is just based on 5. I have a very simple autoencoder that is, the goal of this autoencoder is to reconstruct the number 5. Given the number 5, I have a certain latent representation. I pass 5 through it. It encodes it into that latent representation and decode it back into the 5. But while testing, I'm given this kind of an anomaly, a 6. And unfortunately, we don't have what we want, because again, it's not something that a network has seen. It has no idea what to do with this kind of a patch here in the bottom left corner. You won't get the 6 in this particular situation because the network has not trained on it. Again, this is a very a simple toy example of how we can do anomaly detection. And going back to the goal, we are discussing about how gradients can be used in this particular respect. So why gradients? So let me go back to what we were doing with explanations, right? And try to expand the idea of what gradients were. There, I just very simply said gradients are some weights that show you the importance of certain features. They multiply the features, the kernels essentially, and you get this kind of an importance measure within the network. What actually is happening is that it is telling the network that these are the places that you need to change your knowledge. So it's telling you that knowledge already exists within a network. And if I were to change this particular knowledge, this amount of knowledge in this particular direction, then I could incorporate this within the framework. So going back to the spoonbill flamingo image, you have a spoonbill, but if you had an S-shaped neck, then it would be a flamingo. So you need to change this within data in order to get an output that is flamingo. Right? So it's trying to change the network knowledge, and we were just showcasing it. We were just showing those results instead of actually changing the network knowledge or updating the weights. So let's take a step back and say, okay, now this is very important for us. So in order to change a 5 to a 6, the small changes need to happen within the framework. So where are those changes essentially is the anomaly, right? So how gradients are, instead of having activations as projections, which are showing you that this is the distance, this is the difference between an anomaly and a stationary normal process, what gradients are showing you is the process it requires to change the normal data into an anomalous data. And we are measuring that process and saying that this can be a good measure of an anomaly. It's kind of like a dual problem, the way we are setting it up, where instead of just looking from an activation projection point of view, you're looking at what changes need to happen within the activations in order to get a better activations. And that change is gradients, and that is a way of measuring the distance essentially, because again, we don't have access to this kind of manifold during training, right? During testing. So we have to create this kind of a counterfactual manifold and say that this is the distance between the two. Locally, we need to calculate that distance, and we are saying gradients are a good way of doing that. And that is essentially what we are trying to say in this particular thing. How much of the input does not correspond to the learned information? So in this case, this portion here is the 6. It's present in the 6. The small part here, hopefully you can see my cursor, the small part that should have existed here does not exist in 6. So it's not something that a network knows to learn or has not learned. So it's not able to use that information within the framework itself. So then the question becomes, how much model update is required by this particular input? So in the next slide, basically, it's more of an idea or like a geometric interpretation of what I just mentioned. So let's say we have some kind of a manifold that has already been learned. I'm getting some kind of an X out, which in this case is some kind of a novel data, which is not on top of the, it's projected away from the manifold itself. So what gradients are showing is what change needs to happen within the manifold in order to get it, right? So more and more you go towards that particular change, the amount of change can be the distance. You don't need to know where the manifold is, what the manifold is. All you need to know is the change that needs to happen in order to get to the anomaly. And that is given by the gradient. The process change is given by the gradients. So gradients from different layer capture this abnormality at different abstraction of data. And also gradients provide directional information. We have discussed this before. So gradients are a good feature in order to get this particular distance within the manifold is basically the motivation at this particular point. Now, we can use these gradients in order to constrain as well. So the next couple of slides are more like a proof of concept of the motivation I just mentioned, which is that gradients are a good distance measure. If we were to constrain based on gradients, we'll get good anomaly detection, right? So that we discussed about how anomaly detection requires good constraints and then some statistical measure. So we now just talked about how gradients are a good feature for this kind of uncertainty. So now if I were to constrain based on gradients, I would get a good result. And that's the way of thinking at this point. And this is not something new, right? Momentum, for instance, during training is something, a very simple way of optimization where we don't want to change things too much across the training epochs. If my previous epoch I was moving in a certain direction, I want to continue in that direction as well. I don't want to change it too much is basically the motivation for something like momentum in your back propagation process during training. We want to do the same thing here as well. So instead of constraining the activations, we constrain it based on gradients. The way we do it is by having some kind of a similarity function, a cosine similarity between the previous set of gradients versus the present gradient. And that is subtracted from the loss, which could be a cross entropy loss or anything at that point. And you basically backpropagate the J function. Again, this J is different from what we had during the explainability framework. This is the anomaly detection framework is different, but ideally you're still backpropagating this kind of a loss function in this framework. And there's a few numbers here at this point. You can use a VAE, you can use a convolutional autoencoder. In any case, usually something with a gradient constraint performs better than if you had not put it in, which again is more of a proof of concept. So there's not much, numbers are good. That's all I can say. I don't want to go deep into the numbers itself. The main motivating function or main motivating point here is that gradients give you that distance, and it's a dual distance. Instead of, since you don't have access to the manifold, you can't get the distance directly. So you want to change the manifold as much as possible. So even without knowing what the underlying manifold is, gradients give you access to that kind of information through that process. So using that motivation, if we constrain and get this kind of an anomaly detection, either with VAE or VAE plus grad, which is the second row at this point, or CAE, which is a convolution autoencoder plus the gradient constraint, we get, generally, we get better results. You can use this for anomaly detection, or you can use it for some kind of a condition or corruption detection. So let's say normal is the stop sign, but then you have rainy stop sign. There's rain involved. You have trained using normal or pristine data under sunny conditions, but then during rainy conditions, if you have some kind of data, you should be able to detect the fact that there is rain. Of course, we'll have different sensors, but currently I'm just talking about from a computer vision point of view. In this computer vision point of view, you need to be able to say that I can only give an X amount of trust or X amount of uncertainty, right? Based on the fact that it's rain or haze or something else. Gradients will give you that output. So gradient loss is usually better in terms of these results. Again, we don't want to get lost in the details there. The main idea is that gradients give us this distance, even though the manifold does not exist. Now, let's talk about a more interesting scenario. So previously, during the explanation process, we always talked about backpropagating a prediction with some kind of a contrast class. It's Flamingo, it's Boxer, blah, blah, blah. It could be anything. But in a lot of cases, we don't have access to this information, right? We don't know that a network has trained on a spoonbill. We don't know that a network has trained on Flamingo. I am just going in without knowing anything. As a kid, for instance, I'm just going in without knowing anything. And I still want to be able to get these kind of explanations. So that is something we'll discuss in terms of confounding labels. And we'll do it specifically for the case of out of distribution detection and corruption and adversarial detection as well. So this was a newer paper that we did that came out actually last year. This is 2024 again. So the principle is the same as before, which is that gradients provide a distance measure between the learned representation space and some kind of novel data. So given a learned representation space, and novel data, it projects onto it, but you should not trust this projection. And gradients move towards that novel data, so it can be used as a distance measure. Now, how do we get that gradient? Because in explanation, we saw three different ways, right? We backpropagated a prediction, we backpropagated the negative of the prediction logic, and we backpropagated the loss function. So it's not always clear what we would have to predict for a different application. In anomaly detection, the loss was between the input and its reconstruction. Right. In prediction, there is neither the reconstructed input nor the ground truth. So Q was a flamingo. I just chose it arbitrarily. So it's not like there was a reason for me to choose flamingo. There was no reason for me to choose a boxer. It just gave good results, so I'm showing it to you now. But there's no a very good reason why I would do something like that, right? Because again, novel data, you can't trust the prediction. So there is no ground truth in this particular case. So how do we adjust for that fact? Well, we backpropagate all contrast classes. So if we think about what the output is, we say it's a flamingo, we say it's a spoonbill. From a neural network point of view, it's a one-hot vector. It's a 0, 0, 0, 1 at the flamingo or 1 at the spoonbill that exists. And we can backpropagate this one-hot vector within the contrastive framework, let's say, and get a loss function. But there's no reason to do that. It's just for our understanding. It's just for us to have a better understanding of what the network is showing us, that we can backpropagate this one-hot vector. But we don't need to do that. What if I just backpropagate all once? What if I backpropagate 1, 1, 0, 1, 0, 1, or 1, 1, 1, 0, 0, 0, and so on? That question is not good. That why spoonbill rather than flamingo is not a good question right now, because that question does not exist. So we are moving away from that explainability and saying that I'm just going to backpropagate all once. It doesn't matter. Like, I don't know what the output is. I don't know what the class is. I don't know if it should be a flamingo. So without that knowledge, I'm just going to backpropagate all once. And we call that this kind of a confounding label. So in this particular case, we have the highest amount of uncertainty. If you define, if you think of it as information, all ones at the very end basically has the highest amount of entropy, so which is the highest amount of uncertainty in this particular case. So we are giving it the maximum amount of information during inference to see what is happening. So what are we doing exactly? So we have this kind of a manifold that we start with. If we project a novel data on the manifold, we have a small amount of local information that exists. We know nothing else about this data. But then we are giving a counterfactual class. X dash here is not just a novel data in terms of the data itself, but from a class perspective. I am saying that spoonbill is actually a flamingo. So I mean, correctly means contrastively or incorrectly or counterfactually in this particular case, which is that I am asking the manifold to move to this point without knowing anything about the different things over here. So this distance is not calculated based on the other parts of the manifold, just this local information around this thing. Now, if I backpropagate contrast class 1, it will move by this small amount. If I backpropagate by some other contrast class n, let's say, it's going to move by a huge amount. So the differences between a boxer and a bull mastiff is very small. But between a bull mastiff and a blue jay is very large. Every part of the image is going to be requires changes, right? So that change that needs to happen in that part of the manifold is very large, is basically what this slide is trying to convey. Gradients represent the local required change within the manifold framework. So what does that mean? So explainability, we were trying to have part 3 activations of learned manifold weighted by gradients, essentially. So we were moving between the manifold itself, while right now we are talking about how to move away from the manifold in order to get a kind of a distance. So statistics of gradients with respect to the weights, I'll talk about energy in a little bit, that's the methodology, will be directly used as features in this particular case. So how do we get this? So let's say I have this kind of a X, and then there is this network that is available. I pass the image through the network, I get the final fully connected layer, and I get the final logits at the very end. And I get a loss function by backpropagating all once. It doesn't matter what the prediction is. Let's say y cap or p is the prediction. It could be a spoonbill. Now I backpropagate all once. Again, the question of why is P rather than Q is lost at this point. We are backpropagating why is spoonbill rather than blue jay and this and that and so on. But essentially, we are backpropagating all different ones. There's a huge amount of theory involved of why this actually works. I'm not going to go into details, but the it's in the paper at this particular point. Now, what we use here is basically this backpropagated gradients. And in the next slide, I'll show you the difference within the gradients themselves. So if I take, so there are two steps involved. The first one is we measure the loss between some prediction P and vector of all ones and backpropagate to obtain certain feature. And this particular feature, we're going to just take the energy of these features. At every different layer, there is some kind of gradients that are available. And for every gradient, we just take a simple energy function. We take L2 norm and vectorize, we take a vector of it and put it down into a single number using L2 norm. And this is the output that we have when we have two different data sets. So let's start with discussing about this figure itself, because I think it's a very informative one. Let's say I have a neural network that was trained on MNIST dataset. MNIST is very straightforward, very simple digits that exist. So my in-distribution data is MNIST. In other words, my training dataset of 50,000 images was MNIST. During testing, I take 10,000 images from the test set and I pass it backwards. I pass it forwards. I get certain outputs. Now I take the confounding label, which is all ones, and backpropagate it. And if I take the energy, I don't know if it's visible, but the blue thing here is the gradients from the MNIST dataset at different layers. So this one is convolution, the weights and bias, weights and bias, so on. I believe this was for ResNet 18 architecture, and there's like 29 different modules or something like that in this particular network. So what you're seeing is at each and every layer, you're looking at the gradient energies when you backpropagate this kind of a confounding label. Again, you don't know what to backpropagate at this point, right? That's why we have backpropagated the confounding label. And there is a clear difference between MNIST dataset and an out of distribution data. So a network that has been trained on MNIST, now you suddenly give it the Sun dataset, which is out of distribution. It's not a digit dataset. There's like, I believe it's like a very simple natural images that exist. So given this kind of a dataset and backpropagating this data, my gradients are going to be much higher in this case. This is probably the most egregious example where you have your MNIST dataset has these gradients while the gradients from Sun dataset is very high. The reason you have this as a box and whisker plot is I think there's about 10,000 images. So all the gradients exist within these things. So each of these things is like a point and it exists across this kind of a box and whisker plot. Essentially what this is stating is the amount of change required within a network to include the out of distribution data within the network knowledge is much higher than the amount of required change used to get this kind of MNIST data, which was in distribution. And that's a very intuitive and simple statement to make. But the problem has always been, what do you backpropagate? And the answer is, if you backpropagate this kind of a confounding label, you will get this kind of output where the gradient energies, the magnitudes are very different from each other. So this is, the previous one was just two datasets, MNIST versus Sun dataset, and it was shown for different layers. Now, let's say I'm taking the different layers and just taking a mean out of all of them. And this is essentially how you have it. So MNIST is circled in red. And in almost all cases, your MNIST data set, the results for MNIST are very low. The required change is very low. Required change for other data sets, Tidy ImageNet, LSUN, CIFAR10, SVHN is higher. So the amount of change required is going to be much higher when you're using this gradient. Again, I just want to call back. All we're doing is showing the fact that gradients give you a good distance. It's a required thing, that they are a good source of uncertainty. And we are trying to prove it in these applications. The papers, of course, are from an application point of view, because we have to have like five tables at the very end of a paper to show that this is a good methodology. But the more interesting thing is in the concept itself, which what gradients are giving us for this particular confounding label. The way we do it is basically, I think this works on adversarial, noisy, and out of distribution data. So if you take a deep neural network on some training distribution that has already been trained, we introduce some kind of challenging condition. In this case, we'll talk about three things. We can derive gradient uncertainty on both trained and challenging data, right? So we have a network that has been trained. I'm going to take 10,000 images from MNIST. I'm going to take 10,000 images from a different data set, in this case, 4 challenging data sets. And we can derive the gradient uncertainty by backpropagating the confounding label and taking an L2 distance or a square norm of the gradients. Then we can train a simple edge classifier on top of it to detect whether something is in distribution or something is out of distribution, because there is a change between the two things. There's been more papers where you actually don't even need a new detector. Basically, having some kind of simple constraints, you can say that if it's greater than this or if it's lesser than this, it is going to be an anomaly or it is going to be out of distribution. So in this particular case, we'll show results from this setup, and we'll show it on 3 separate results. So let us take a look at the first one, which is gradient-based uncertainty in this kind of an adversarial setting. So we'll start off with this. Hopefully, all of us are aware of adversarial images. I think it was back in 2013 or 2014 when it was first brought to light. Given this kind of a panda image on a trained neural network with 57% confidence, you can say a network used to say that this is a panda. But then you put this kind of an indistinguishable amount of noise on top of the panda, and the results are they turn around completely, and the network says that it's a given with 99% confidence. This is not something that we want. Ideally, we still wanted a panda result with a good confidence, but unfortunately, that is not what you're seeing. You're seeing a given with a very high confidence, and our entire goal of the tutorial is to talk about what happens at inference and to derive robustness. So this is a huge issue. We want to be able to detect these kind of results when it's out of distribution or when it's adversarial setting. And using gradients, you will be able to get the gradient results essentially based on different architectures and different attacks. Again, the numbers by themselves are not as interesting. It's a required thing to have it at the very end, but essentially we'll be able to get a good result based on the gradients and more importantly, back propagating the confounding labels, which is all once, and you can do it on different attacks. And since then, I think we have other adaptive attacks as well that it works quite nicely on. So that was about adversarial detection. Maybe there's other kinds of detection, right? Our goal is not just to have a single application. We want to make sure that gradients work on multiple applications because, again, the goal is uncertainty. So let's say instead of anomaly out of distribution detection, we have the corruption detection that we discussed before. Cure TSR is basically given the simple clean images, and you add a noise, some kind of challenging conditions on top of it. You have these kind of 14, I believe there's 12 challenging conditions on top of it, while Cyphart&C or ImageNet-C essentially has about 19 different corruptions on top of it. I think we're showing about 8 over here. Given a normal data, you can add this Gaussian noise, defocus blur, Gaussian blur, and so on. So the good thing about these data sets is that it gives you different levels of corruption. Take Cyphart&C, for instance, on the left-hand side. You have 19 different corruptions, like Gaussian noise, defocus blur, Gaussian blur, and so on. And within each corruption, you have 5 different noise types, noise levels. So there's level 1, which is a slight amount of noise that is added, and level 5, which is a huge amount of noise that is added on top of the data itself in order to get some results. So let's take a look at the results based on these noise types. So we'll start off with Cyphart&C, trying to understand Cyphart&C in this particular case. Level 1, small amount of noise. Level 5, huge amount of noise. So in this particular setting, we are detecting challenging conditions. That is, we want to say that something has Gaussian noise. We want to say that something has some kind of a codec error or any other corruption. Usually level 5 is very easy, very straightforward, because there's more amount of noise involved. So the distance or the change between the novel data and the pristine conditions is very large, and anything and everything will probably work in such settings. The more difficult part is the level 1 setting, which is level 1 and level 2 settings, where the change between the distorted data and the pristine data is not as high. So we should be able to detect better in the first few levels than we do in the last few levels. And in Seifert and C, you can see that gradients basically work in all conditions. In this case, the one on the right-hand side is the gradient-based methodology, while the left-hand side is Mahalanobis distance, which is a very popular, and it works very well in terms of adversarial and out of distribution and stuff like that. It's usually better in such cases. The more interesting thing comes in the Seifert and, the QRTSR. Again, these are more real world settings for autonomous driving rather than Seifert and C, which is based on a data set that exists and we add noise. In this particular case, it works very well with level 1 and level 2. I believe in only one case, Mahalanobis is better. We are showing AUROC results. That's why it seems inflated. The 99 point it's very inflated. But if you look at accuracy, it's much lesser in this case. When you go to the more difficult scenarios, you'll see that the gradients does not work. More easier scenarios, you'll see that gradients performs as well as activations, which is the Mahalanobis distance, which is it is based on. But the more difficult scenarios, which is the level 1 and level 2, usually gradients are a better source of uncertainty than the activations and some distance measures within the activations themselves. Same thing with the last one as well, which is out of distribution detection. So out of distribution detection is if we have a big train set, let's say MNIST, out of distribution is basically the source is different from the testing data. So instead of saying that this is the data that we have trained on, we are now saying, okay, this is the data that the network has not seen. So this goes back to the first slide that we had. So the network has not seen this source of data, so you should not trust any output that is coming out of it, or there needs to be higher uncertainty for this particular case. So based on detection accuracy, AUROC and AUPR, the results for out of distribution detection are also good, essentially. Again, these are numbers based on different methodologies that we have seen before, plus the R's part here is, of course, the gradients here. And under different scenarios, gradients do better. Gradients do better and work better in terms of the out of distribution data. Again, the overall goal is to say that gradients are a good measure of distance when your underlying distribution is not known. With that, I think we can move to the next part. And this is more of a case study of introspective learning. So till this point, we have just discussed uncertainty as this idea of distance that exists, where we'll be using this distance in order to get a good measure for a particular application, right? So all we were doing in the previous things was detecting something. We were detecting the fact that something is either out of distribution or adversarial or corruption. Let's say corruption, for instance. Let's expand on the corruption part. So we were saying that a particular image is afflicted with Gaussian blur, and this was our output. We were saying that this was the problem, this exists. Now, what we want to do, robustness is not just detection. We want to make sure that we remove that portion. Maybe remove is not the right word, but we want to ignore that portion. We want to ignore the Gaussian blur in order to get a good output, in order to make the correct prediction. Until this point, we have not changed the prediction at all. Explanation, we were seeing the results for the prediction, and in uncertainty, we were detecting whether this prediction can be is something that is trustworthy based on some distance that we found when the manifold is not present. At this point, in this case study, we will see how the predictions can also be changed essentially with this fact. So this was from 2 years back, something called introspective learning. So I'll talk about what introspective learning is to start off with, and then discuss how we can make, how we are doing it. So this is an image that we saw before, and there's a reason we put this image here, right? It was carefully selected. It's difficult to see even from a human perspective, which of them are blueberry muffins and which of them are puppies. How do we overcome this challenge? We kind of look at it for a couple of minutes, for a few seconds, to say, okay, this is a muffin, this is a puppy. It's not immediately apparent to us just by a first glance whether something is a muffin or whether something is a puppy. So you can now ask yourselves, why am I being shown the slide? Why images of muffins rather than pastries? If I'd put pastries here, this would have been very simple. You wouldn't have actually had to introspect or try to understand. So what if the dog was a bull mastiff? Again, that also would have been very straightforward. The answer for that would have been very straightforward. There's a fine-grained difference between all these images, and that is why this image is being shown here. And the way we answer this question is by introspection. So let's actually define what introspection is, more from a very umbrella point of view rather than technical definition. So introspective learning is a two-stage approach for inference that combines visual sensing and reasoning. So this is introspection itself is a very philosophical definition, and it has two things. There's sensing and there is reflection. Sensing is very straightforward. We look at something and we make immediate decisions. I think the neuroscience point of view is about in 80 milliseconds, I can look at a particular scene and I can make a lot of decisions about a particular scene. But it's a very shallow decision that we make when we look at this kind of a sensing methodology. This is when reflection comes in. So let me discuss just this image that is there on the slides. Given, let's say we are a kid again, given this kind of a spoonbill, I can look at the the pink feather, straight beak, and all these different aspects within the spoonbill image and get certain output. And these are the different features that I can get out of it in order to make the classification as a spoonbill. So this is like a sensing output. Now, reflection is when I start asking, when I start questioning myself. And I ask, okay, why is it a spoonbill rather than flamingo? Why is it a spoonbill rather than a crane? Why is it a spoonbill rather than a pig? So all these different ideas, all these different outputs is something that I can question and I can reflect on my decision. I can reflect on my data, I can reflect on my decision, and then I can come to hopefully a better decision. And that essentially is the introspective learning part, where instead of just giving a short, simple solution, I'm using a more refined solution. In terms of, again, philosophically, there's different ways of thinking about it. I think a few years back, Yoshua Bengio has this kind of a system 1, system 2 architecture, where the system 1 is a very simple way of getting the outputs, while system 2 is you have to work for your solutions. You have to plan and reason, basically, in order to get a solution. And this is kind of a way of thinking about how to do that. But again, those are very esoteric. So instead of concentrating on that, what I would like to concentrate on is basically having this kind of a more technical definition for what introspection is going to be. So goal is to simulate introspection in neural networks. We think of neural networks as the simple, straightforward, forward pass architectures where given an image, I can get an output by getting these activations, by getting these different outputs, intermediate outputs within the network. So the way we would define it is we define introspections as answers to logical and targeted questions. The good thing is, in explainability, we already talked about the targeted questions. We can have 3 different paradigms of targeted questions. Again, I'm not sure if at the time I mentioned it. So there are 3 different paradigms of the questions themselves, but the number of questions is very high. It could be 2 to the power of n. So why bull mastiff rather than a boxer is one question. Why bull mastiff rather than a flamingo is another question. Why bull mastiff rather than this and this and this can be other questions. So there's a large number of questions that we can ask and get the outputs for in these scenarios. So putting that here, we say that goal is to simulate introspection, and our definition is a contrastive definition. So introspection answers questions of the form YP rather than Q. So we are reflecting within ourselves and asking some kind of questions that make logical sense. Spoonbill and flamingo have similar characteristics. So we can ask this question and expect a good answer in this particular scenario. So this would be a contrastive definition. A technical definition is going back to the gradients. Again, gradients are the thing that is that's holding the previous part and this part together, which is that given a network, some data point X and a prediction Y cap of P, introspection is the measurement of change induced in the network parameters when label Q is introduced as the label for X. Again, the label Q, completely incorrect. We know that something is a spoon bill, yet we give a label for flamingo. We know it's a spoon bill, yet we try to backpropagate all different ones, right? So we know it's incorrect, but it doesn't matter. It is giving us valuable information during inference, and we lack this kind of information during inference. So we will take everything we can get at this particular point, and we'll be using this kind of introspection as our resultant. So let's actually, so till now, we have looked at gradients as explanations. Sorry, if you had a... So in explanations, since we are looking at the images, we know to ask these kind of questions. In this point, we don't know where Q is coming from, so we backpropagate all once, essentially. So it's literally the confounding label, which is the one n. So it's instead of a one hot vector, backpropagating 1, 1, 1, 1, 1, like 1,000 vector of all ones in this case. So going back to the MNIST image, like I don't think I've actually shown you gradients until this particular point. We've only seen gradients as a function of activations, which is explanations, and how well they work in application, which is the art of distribution and all these other scenarios, right? So for a well-trained network, the gradients are actually very sparse and they're very informative. So given this input image here of A5, that is what is there on the left-hand side. A network has been trained again with 50,000 images from MNIST. Now I pass the image 5 through the network. If I backpropagate 0, okay, so this particular network, I think it was like 2 convolution layers and 1 fully connected layer. And I'm taking the fully connected layer, which is a 50 cross 10 matrix, and showing it here. The reason 10 exists on the y-axis is because MNIST has 10 different classes. So each row here corresponds to that one particular class, while the network itself, while I think the layer before the fully connected layer, or the layer before the logits, is like 50. Hence, you have like 50 cross 10 as a matrix here. What you will notice is that when I backpropagate 0 as a contrast class, you'll find gradients at only 2 points. It'll be at 0, you'll have different gradients here, and it'll be at 5. So what this is telling you is that if you think of this from a linear algebra perspective, again, trying to do this in a 10-dimensional is impossible. Think of it from a 3-dimensional perspective. What is happening is that one of your basis functions is changing. 0 is moving towards the data, while 5 is moving away from the data. And that's why you have changes in only 2 of these filters, or 2 of these weights, at 0 and 5. So you're getting a lot of information about just 2 different weight functions in this particular weight matrix. Now, if I backpropagate 1, you'll have changes at 5, and you will have changes at 1, which is basically the small changes that are happening at these 2 points. If I backpropagate 2, I get the same thing. 4. If I backpropagate at 5, it's actually very interesting, because what it changes is 5 needs to come closer, and the next best guess needs to go further away, because you're basically you want a better confidence, you want a better solution. So this is how the gradients are going to look like for a well-trained solution. And one of the reasons I'm showing it in MNIST is because it's kind of the definition of a well-trained network, because it is the simplest data set. It gives very, very good result. If I do the same thing for something like ImageNet, which you can try, you won't get as good results as this. There's going to be a lot of artifacts that exist within this this part over here, and so on. So again, MNIST has been chosen for this particular slide because it is giving you the best possible trained network there is. So the point again here is that these kind of features are very informative and very sparse, which is exactly what we want. Because from this point onwards, we're not just thinking about these gradients as something that we'll be just collapsing into one L2 norm. Rather, we'll be using them as particular features. Again, I'm not going to go through the definitions completely, but or the math completely. But this actually harkens back to our part 1, where we said that during inference, given a single network and a single data point, we can get information about many other classes. So in this case, for backpropagate yi and y cap, let's say, I have terminologies that have yi. which in this case is the introspective class or the contrast class, and YY cap, which in this case is P, which is the prediction. So I have access to both these information. And let's think about the robustness aspect. Let's say I have the image which is out of distribution, or have added noise to my particular image. In a simple sensing or simple neural network point of view, if I want to change the prediction, I just need to add enough noise to the image to get the wrong prediction. But if I'm using gradients features, I need to do two things. Not only do I need to change do I need to add enough noise to change the original prediction, I also need to add enough noise to make sure that the nearest class or the contrast class also gets changed. Right? That is exactly what we saw in these settings. Gradients are not just a function of a single class, they're a function of multiple classes. And if I backpropagate all once, it's going to be a function of all different classes. So the amount of noise required to change the prediction when we are using gradients as features is much, much higher than if I were just using a simple feed-forward process, which is the sensing process in this particular thing. So that is exactly what is here. Any change in class requires change in relationship between yi and y cap. It's not just a single class. Multiple relationships have to be changed. And this, again, is just for a single thing. What if I backpropagate, let's say, all once, which I did before, and we now look at this relationship as the way in order to achieve robustness. So given this kind of, this is the exact slide that we had before. Now we are again backpropagating confounding labels. Till now I talked about backpropagating contrast class, but confounding labels also essentially it's the same thing. There's a slight amount of approximation that we'll need to do. And if we do that, then we can backpropagate all once, which is this confounding label. Again, I won't go into the theory aspect of it, but we can use these gradients. Before, what we did was we used these gradients, collapsed them into a single number, which is the L2 norm, in order to get results. But now, let's actually use and create this kind of an introspective network or a very simple network on top of our this thing. So sensing network, let's say, is a large foundation model or a transformer architecture. What we have noticed is by extracting gradients and training a very simple 3-layer MLP, we can get a prediction, which is the introspective prediction, right? So the first part of this case study, we had the sensing, reflection, and it was a very, again, a very esoteric one with Spoonbill and asking these kind of questions. The goal was to simulate it using gradients, and that is exactly what we are doing here. The sensing part is I'm getting some output, which is y cap. Then I'm backpropagating all once within this framework in order to get these kind of introspective or reflective features. I'm using those reflective features in a next stage, which is the second stage in my inference process, which is going to be this kind of an introspective network. How do I do this? I just backpropagate it, and I take all the weights, I concatenate, I take the gradients of all the weights and concatenate them. By gradient of all the weights, I mean this. These are the things that we are concatenating. I'm going to take all these particular weights, the changes that are happening, and I'll concatenate into a specific RX1 for a particular image. I can do this for the entire training set. For, let's say, if I have 50,000 images, I can use the gradients for 50,000 images and train this very simple MLP architecture. You don't need 50,000 at all. In fact, in our experiments, like a very small 5% subset gave us very good or similar results as to the 50,000 images. So you can, a small set of images can be used to train this MLP architecture to give this output as y tilde. So this is kind of a way in which we are taking introspective settings from the esoteric slide one and trying to put it into a neural network setting. So this gives us this kind of a robustness. So how do we define robustness? Two things: generalizability and calibration. Because that is how we talked about in the adversarial setting as well, right? In adversarial setting, the prediction changed. We don't want it to change. We want the increased accuracy on OOD data and the calibration. So I'll talk about calibration in the next slide, but the problem that we saw in the adversarial image was that the confidence was like 99% confidence on a completely incorrect result. So we want to make sure that our results are generalizable or our networks are generalizable and our network is well calibrated. So from this setting, let me just very briefly talk about what calibration is. It's a very nice concept that has existed in statistics quite a lot. Back in 2017, actually, this is the wrong citation for this, but I think the citation GUO, the one of the authors, the first author was Guo. So they discovered that larger the architecture, worse the calibration is going to be. So let's look at the bottom two graphs over here. The left-hand side is LeanNet architecture, which was 1998, a very simple, just a bunch of convolution layers stacked on top of each other. If I have 10,000 images and I pass them through LeanNet architecture, and I basically look at the confidences, and I make bins of confidence. So let's say 10,000 images, most of these images are classified with about 0.8 to 0.1. That is, they're classified between 80% to 100% confidence. You put them in this particular bin. Now, if it's classified between 60 to 80%, you put them in this particular bin, and so on. You can have all these bins, and you can look at the accuracy within those bins. And intuitively, what you would imagine is that if I am confident with 80% on 100 images, my accuracy on those 100 images should be 80%. Or 80 images should be classified correctly, while 20 images should be classified incorrectly. That is what we see here in the LeanNet architecture. You see that there is this kind of a rising step function. Accuracy is on the y-axis, while confidence is on the x-axis. So for a bin that is between 0.2 and 0.4, the accuracy between 0.2 0.4 is the same as the confidence that exists. But let's start looking at the ResNet architecture. And by the way, this problem has become even worse. So on the ResNet architecture, what you will notice is that your confidences are very high for a large number of results here on the right-hand side, while the gap between accuracy and confidence is much higher on the other regions. This is not what you want. What you ideally want is on the left-hand side, and this is not the result. So this is basically calibration. There are different methodologies in order to correct this. The most important one is temperature scaling. I'm sure most of you have heard about it. It's essentially you scale your outputs with certain temperature, and this temperature has to be learned beforehand. This is not something we can do during testing, because we don't have access to that capital T or that temperature, because you need it while you had trained the network. And if you try to guess what the temperature is, it's actually very different between data sets. It's not always easy to use temperature scaling during inference when you never trained it as a hyperparameter. So what we notice when you do introspection is that the accuracy increased while the calibration also got better. And that is what we see here on the graphs. Let's look at the left-hand graph on Cipher10C. We have 4 architectures, like all ResNet architectures. If we introspect on them, the results increase, performance accuracy increases, and your expected calibration error, which is a sum of all those gaps that we saw, decreased, which is exactly what you want. In fact, the decrease was about 43%. There was a huge decrease in terms of calibration. Or I'm saying decrease, or the calibration error decreased, so your calibration got better in this thing. So in this particular graph, ideally, you want all your networks to be in top left corner, while existing ones are usually in the bottom right corner. So without doing many changes and looking at the gradients as features, it gives you good generalizability and calibration. Again, the data set is Cipher10C and Cipher10Cure. And on these data sets, we are talking about the ones with the corrupted data, 19 different corruptions, 5 different challenge levels. So essentially, Cipher10C has about 950,000 images, and same thing with Cipher10Cure as well in the test set. And this is like an aggregate of all these results. Introspection also works on, it doesn't matter how you're trained your sensing network, which is very important, because there's new strategies for training, right? You can have self-supervised learning, you can have transformer architectures, you can have very good ways of trying to get a good sensing network, which is fine. You want a good sensing network. But the point is that once you introspect on top of it, or once you get these gradient features, it always helps you. Especially when there's these kind of out of distribution or corrupted data during inference, it helps you get a more generalizable result. In all these cases, the accuracy increases. I think only in the last one, the accuracy is the same with and without introspection. The accuracy is like 89%. But in this particular case, the calibration error decreased by about 43%. Actually, I have it as 40% in this particular case for Office data set. Again, the point here is in trying to say that when you introspect on top of a sensing network, it helps you whenever there is novel data involved. When there's no novel data involved in our experiments, there was no difference in terms of the output. The reason was that the gradients themselves was zero everywhere. It was very sparse, and you did not need this kind of a second stage to give you a different result. But when the data is novel or there is corruption, you have a large amount of increase in generalizability as well as calibration. One of my favorite applications is actually image quality assessment. Unfortunately, in this particular thing, we did not have time to go through this thing. We have an entire part that is dedicated to like the contrastive explanations for image quality assessment. It's this idea that given an image that has been corrupted, how would humans rate this? And this is very important if you're uploading images to, let's say, Instagram or something like that, where usually people upload, look at an image, decide, oh, is this good, is this bad, and then upload it. But if we were to automate this entire process, that is given by image quality assessment. Again, image quality assessment with introspection is better. Out of distribution with introspection is better. Active learning with introspection is better. The goal of this particular slide is just to show that it doesn't matter what kind of downstream tasks you have, the plugin nature is sufficient to have a good introspective result, is the goal of this particular slide. Any task you have, if you have novel data, you would rather have introspection in your framework rather than without. So that brings an end to the fourth one, which is the uncertainty part. I think I'll have to hurry a little bit in the intervenability part, which is going to be part 4. All right, so we discussed explainability, we discussed uncertainty, and even while speaking, in many cases, I felt like these two seemed disconnected. We talked about all these visual features that we saw in the explainability part, but in uncertainty, we started having discussions about, okay, confounding label. So there's no contrast class, it's all ones. And then we showed numbers, which basically meant, okay, we are proving that it's uncertainty, we are proving a concept based on applications, which is always a problem, which is not good because we cannot always control everything that is happening within applications. And just saying that, oh, this is the concept that changed, hence it's a good concept, it's not a very good argument to make. But again, that's how we have to write papers, because at the end of the day, we need these kind of applications to demonstrate that the concept is working. So this part tries to combine the two things. We'll discuss how do we evaluate explanations and try to look at it in terms of uncertainty by making interventions. Now that sentence was a mouthful, so instead of I'll go through that sentence and talk a little bit more about in detail what exactly it is. Now, the problem that we have with this particular part is the definition of intervenability is not very easy to describe. The easiest way, if you have heard about interventions, it's basically coming from the causality framework. You want to make interventions within some entity in order to see what the outputs are, in order to judge the effect of this particular entity, which is it a causal factor, is a non-causal factor? And it's that definition is a little bit straightforward. But these days, the definition is a little bit more murkier with privacy, interpretability, prompting, and benchmarking that comes into picture. So what we'll do is, in fact, just have one sentence each for these definitions to try to understand what intervenability is from all these points of view, instead of just thinking from one particular aspect. So this here, the definition is going to remain consistent. Intervenability is essentially the amenability of neural network decisions to human interventions. It's as simple as that. Given a neural network, how good is a network? How well does a network take the fact that I can make interventions on top of data? In causality, interventions in data are manipulations that are designed to test for causal factors. This particular reference, it's an excellent paper that goes through towards causal representation learning. Came out a few years back. it's one of the best papers in terms of trying to understand causality and look at the literature landscape for causality. So ideally, they define interventions as some manipulations that can happen that are specifically designed to test for causal factors. And on images, this definition does not make as much sense. But think of tabular data. You have these kind of hotel data sets. You have these kind of some kind of tabular data that is there. You can make small changes within the factors. You can eliminate a certain factor and see how the network has changed its results. Again, doing the same thing on images is very hard. Let's say on medical data sets, you can't introduce a certain disease into a CT scan, right? Just to see what the intervention is, just to see what the outputs are going to be. But it's more easier to understand it differently. And the goal in causality is to assess. Now, there can be a different definition of intervenability, which is privacy, and the goal there is to assure. In this case, intervenability aims at the possibility for parties involved in any privacy-relevant data processing to interfere with the process, with the ongoing or planned process. So let's say I have a huge data set and of medical data set, and everybody has given consent. But the way if you have the way it's designed, these medical data sets, is that I, as a patient, can come in and say that, okay, I don't want my data to be part of this network anymore. I don't want to be part of the study anymore. In which case, you have to remove the data. Removing the data is simple, but you have networks that have already learned, that have a huge amount of knowledge about a certain problem based on your data. So how do we unlearn that? So there is a huge, in I think the last year's NeurIPS, there was an entire challenge that was dedicated to something called machine unlearning, where essentially, given a certain data point, you wanted to remove that, the effect that that data point had on the network itself. So, and this is the goal of privacy in this case. Your intervention is to promote privacy. And in the previous thing, it was about getting a better result, right? In this case, possibly your results are going to get worse because you're removing certain data, but you still have to do it. And this is where again, the definition of intervenability is quite murky. Now, the interpretation is, again, it has its own kind of intervenability. We'll talk a lot more about this later on, so I'll hold off on talking about this for now. Then the last one is benchmarking. So benchmarking is also the amenability of a network to human interventions, right? We talked about corruptions, we talked about out of distribution, we talked about all the changes that can happen within data. Some of them are forced. So essentially, if you have an autonomous vehicle setting, you cannot always control the rain. You cannot control the snow that happens. So there is a huge amount of intervention that is happening. But sometimes, in order to test robustness, we ourselves, we introduce these kind of challenges within the data to see what the output is. So technically, we are intervening within the data to see what the output is for this particular algorithm, right? So new benchmarks were proposed to specifically test generalization of classification and detection methods to simple algorithmically generated interventions. Or these days, you can have more complex algorithmically generated interventions as well. But the goal in intervention in this particular definition is to verify. We want to see that when there is some kind of an intervention that has happened, how a network changes its output. I don't think I have the other one, which is prompting, but prompting is also kind of an intervention. If you have a large language model and you're prompting it, you get certain answer and you change your prompt a little bit in order to force the network to give you a different solution. You're intervening within its decision-making process. You might think that you're getting a good solution and you want this solution, but in fact, you are placing it, or you're taking the network away and away from its comfort zone. And how good that is dependent on how the network is trained itself. But the more prompts that you're giving, the worse your worse your comfort zone of your network is going to be. All of them are certain definitions of intervenability. So again, we won't have time to go through all different ways of thinking about what intervenability is. And again, the goal for this was to try to connect two parts, which was connect the explainability with the uncertainty using intervenability. So what we'll discuss is specifically the third part here, which is interpret in terms of interpretability. So let's start with trying to understand explanations and how we evaluate these kind of explanations. So we have this image. This is a different spoonbill, but trust me, this is still a spoonbill. So let's say I have two different kinds of explanations that can exist. SX1 and SX2 are two different explanations. This is from the GradCamp paper, GradCamp plus paper, sorry, which was at WACV about a few years back. So SX1 was from GradCamp, SX2 is from GradCamp plus. Now, the question is, how do we say one is better than the other? Because at the end of the day, we want to be able to evaluate our explanations and say that my explanations is better than yours, essentially. So how do we objectively verify this? The simplest answer is you can get a bunch of people in a room and ask them, okay, which is better? But we're talking about like hundreds of thousands of images, hundreds of thousands of explanations. It's not easy to get that kind of a subjective verification. So you have to design these objective measures. So the simplest method is to basically take these explanations and mask them. You can mask this entire image based on the explanation. This is the heat map. This was the heat map. And you would have masked this certain explanation over here. You would have masked this explanation here. And you pass it back within the network. Maybe SX1 is going to give you a crane, but SX2 masked image is going to give you a spoonbill. Right. So now you can say that SX2 is better than SX1. In fact, this is one of the ways that the authors from this paper did this. They said, our method is better than yours, because when we pass it back within the network, our results are going to be better. So if across n images, the expectation of y given SX2, y is spoonbill in this particular case, or your prediction, SX2 is this explanation masked data. If one is greater than the other, then maybe that particular explanation is better, or is more reliable, basically, than your image. But there are problems with this particular way of trying to understand. And the reason is we are intervening within data, right? So look at this particular image on the left-hand side. You assume that a network that has seen this kind of data of birds has seen this kind of a spoonbill. Has it seen this mass data? Probably not. And yet you're passing it through the network and asking for a result. So you have introduced a huge amount of uncertainty within the data in the guise of trying to evaluate my explanation. And you're using this as a methodology to say one is better than the other. So there are problems with this framework. So let's try to create a mathematical framework for what I just mentioned. So this is a new paper. It is currently in the review process, at the end stage of the review process, essentially, and should be available in a few days. So let's say I have an explanatory technique. This is the GradCam explanation for this bull mastiff image. You see here, this is the exact image that we had from before. The goal, or not the goal, what intervenability does is it tells us that there is an uncertainty associated with the explanation. We think of uncertainty, again, I mentioned before, the definition of uncertainty we used before was very, very narrow. It was just a distance from the data to some kind of a manifold, which was single pass uncertainty. But that is not true uncertainty. That's not the full thing, right? So an explanation also has uncertainty. So a network has looked at this image and decided that these are the images, these are the small regions or features that it has used in order to make a decision. But then it's second guessing itself. It's thinking, okay, why have I not used a snout? If you look at the image here, the red region is that it's more informative, it's more explainable, essentially. But the snout is not as red as the mouth that is below it. So it needs to be uncertain about this, because the snout is important. Different dogs have different kinds of snouts. And essentially, you would assume that certain snouts inform the decision. So ideally, you want to have the snout as part of your explanation, but it was not doing it. So you have some uncertainty that is associated with the explanation itself. So there's uncertainty in answering why bull mastiff. Intervenability helps us getting to this part. We intervene on data in order to help us say that the snout is the uncertain portion within this particular image. So if we have an explanation of prediction, we'll have an uncertainty of the explanation as well. Because again, it's not a causal process. There is uncertainty associated with this thing. Let's try to have a mathematical framework for what this uncertainty is. So let's say y given Sx. Y is the prediction given some explanation masked image. Now you can have, I'm just using explanation mask, but there's different metrics of explanations. There's insertion metric, deletion metric. So it can be anything where there's some kind of intervention on top of data, and you have that mask portion over here. So when you have this masked portion, you have your variance, and we discussed this during the uncertainty portion. Different SX will have different outputs. So essentially, you can have a variance across all these outputs. You can use variance decomposition to say variance of expectation plus expectation of variance. The exact definitions are given here. Y is prediction. The variance of Y is variance of prediction. Variance of Y given Sx is variance of prediction given certain intervention. Sx we are just using as this kind of an explanation mask, but it could be any kind of an intervention. Sx is the subset of data here, and you have expectation of class and then the variance of class given all other residuals. That is basically, the residuals is basically what the second terminology here is giving you. Now, let's think about how we evaluated the explanations. We create this mask, we pass it through the image, and we pick the best explanation, or we refine our explanatory framework based on getting a better number, based on the spoonbill remaining a spoonbill. So what we are doing, in fact, is we are making this 0. Expectation of the variance of expectation of Y given Sx is 0. So presumably the GradCamp++, the authors in GradCamp++, they created an algorithm. They saw that the algorithm iteration 1 had this as crate, and then they changed it to have spoonbill as this thing. So you have inadvertently, what you have done is get this kind of if you think of it from this framework, your first element here, your first result has become 0. Again, the explanation itself is very good, but the problem is in how we are evaluating this explanation. So the observation here is that visual explanations are evaluated to partially reduce the predictive uncertainty in a neural network. And this is a very important observation. What we are doing is not an explanation. What we are doing is just we are reducing uncertainty of a network, and we are saying that that is the explanation. Again, the definition, that particular definition, is up to you whether you would like your explanation to be something that reduces uncertainty or if it's something else. But essentially, that is what we have been doing in terms of evaluating explanations. We are just reducing the predictive uncertainty and saying whatever explanation reduces the predictive uncertainty is the best explanation, is essentially what we have been doing. But we have not completely reduced the predictive uncertainty. We have only partially reduced this predictive uncertainty because we have made the first term 0, or ideally we want to make the first term 0 when we are designing a methodology, but we're not really worried about the second portion. Let's look at what the second portion is. The variance of Y given Sx is the variance of class given all other residuals. That is, okay, why is this explanation Sx1 like this? Maybe there's a small pixel on top which should have been highlighted, which is not highlighted. So that's the residual. That is a counterfactual residual, which is like, okay, this might have been there, or this should have been there. This pixel should have been highlighted. This snout should have been highlighted. That is the residual in this particular case. So another key observation here is that uncertainty in explainability occurs due to all combination of features that the explanation did not attribute to the network's decision. It could have chosen the snout, but chose not to use the snout. So why is the question, right? So that is where the uncertainty comes from. And the reason we are building up to all this is it's a method of combining or comparing between explanations, the uncertainty itself. So the effect of a chosen intervention can be measured based on all the interventions that are not chosen. Again, everything that we have talked about in the tutorial is more like from a dual perspective, even the gradients, right? So instead of directly looking at the distance between activations, we kind of said that these are changes which are required. So we kept on moving the manifold a little bit and said, oh, this distance is the gradients, this is some of these gradients. Now we are saying that any kind of a chosen intervention, we chose this particular interventions, but we missed out on choosing all other interventions. Why? And these, the effect of these other interventions is basically where the uncertainty is derived from, or we are getting this kind of an uncertainty. So again, this is going back to that particular aspect. Given this image of a dog, we have explanation of the face itself. Snout is not highlighted. Maybe snout is an important part. Snout is an important characteristic that is used to differentiate against other dogs. Hence, there is uncertainty on why this feature is not included in the attribution. It should have been attributed. And the fact that it is not is a way for us to compare between explanations. So the problem, of course, is that these not chosen features are intractable. Like I can go up and say I can put one pixel and highlight it as yellow. I can take the same pixels, highlight it as red. So those are two counterfactuals. I can do this across the entire image, and each of those things can be, it's an 8-bit image, so it's 2 to the power of 255 or something like that in terms of the number of interventions that are possible. So it's an intractable set of features. Good thing for us, however, is that we have access to these kind of counterfactual explanations. I'm using explanations here, but essentially it could be any kind of counterfactual features. This gives us information about all the non-chosen attributes, right? It's like the difference between spoonbill and flamingo was this particular neck. Those are the important features that it should have seen in order to make a decision. So I can take all those features and use them as my tractable features in this particular case. So I can make a finite set of features that I can use. So let's say SX1 was this kind of one contrastive example, SX2 was this kind of second contrastive explanation. And if I have N, I can have SXN as a nth contrastive explanation or intervention, and have access to a finite set of interventions that are available. And all I need to do is now take a variance across these finite set of explanations. And by doing this, I get the previous result. This is ideally what we get from the result. If I take across all 1,000 and I normalize it, this is what the result essentially looks like. So going back, why did we go through all this? We wanted to answer the question, is GradCam better than GradCam++? Is a Swin transformer more reliable than VGG16? Because again, there's two things that are happening here. The explanations themselves are changing, but also the network that is giving the results is also changing. So we need some kind of an objective quantification of what these intervention residuals give us. So we'll show this in terms of results instead of showing the numbers, because again, the paper is still not out yet, and it'll be out in a few days, but we'll not show the numbers, we'll only show what the results look like. So these are randomly chosen images from ImageNet dataset. We have two measures here that we'll discuss. One is the intersection over union, and the other one is the signal to noise ratio. So let's talk about the first one, intersection over union. Let's say I have access to GradCam explanation, the visual explanation of why something, and I have access to its uncertainty. What we notice is that when your prediction is incorrect, there's more overlap between GradCam and its uncertainty. That is saying that a network is, I have it here, higher the IOU, higher the uncertainty in explanation, or less trustworthy is the prediction. What is happening essentially is that a network is uncertain about the same regions of the image that it used to make the prediction. So if you say that this particular image here of a mosque was using the dome to make an explanation, if it is uncertain about the same regions in order to make the explanation, then it is not good. Right. So it essentially is telling you that it is less trustworthy because it's using the same features that it's uncertain on in order to explain its particular decision. So that is one metric in terms of IOU. The next metric that we'll use to differentiate between, let's say, something like a Swin transformer and VGG16 is something like a signal to noise ratio. This is an image we have seen. So from a VGG16, this is the explanation for a dog, and this is the uncertainty. Using a transformer architecture, this is what it looks like. The explanation is a little bit more covered, while the uncertainty, before it used to be on top for the VG16, right? It's not. But what you see in Swin transformer is apparently it's more uncertain about where the explanation is ending, which also makes sense. This is how it is. Now, let's say I add a lot of noise and get some kind of an incorrect prediction. We see a huge amount of dispersal in terms of the explanation as well as the uncertainties. And this dispersal itself can be used as a metric, which is a signal to noise ratio of the results. So instead of just visually saying that one, let's say Swin transformer is better than VG16, or saying GradCam is better, GradCam++ is greater than GradCam, we can have these objective numbers that help us tell us what the results are. Let's actually look at the images in a little bit more detail. So one way of thinking about it is on incorrect predictions, the overlap of explanation and uncertainty is higher. So currently I'm showing the second image here. Hopefully this is visible. Yes, so this is the image of an eagle. And the explanation is basically looking at the base of the beak in this particular case. GradCam is kind of going around it and showing you that while it's quite certain of the region it's using to make its explanation, around it, it's a little bit more difficult. But if you look at GradCam++, it is showing you that it's a little bit more uncertain about the same region that it is making its prediction. Again, there could be philosophical explanations for why one is better than the other. You should not always be very confident about your predictions. You should be uncertain about your predictions, and that's how you stop hallucination. So from that respect, you could argue that GradCam++ is better than GradCam because it's not as certain as GradCam, right? So again, these are arguments you can make between one and the other, and having this kind of uncertainty gives you this this nice objective metric where you can use one, where you can say that one is better than the other. So let's look at something which is incorrect. So in this case, the network predicted basically an eagle, so everything was correct. But then when I'm looking at this particular scenario now, where this image I think was predicted as a dog sled, which is incorrect, your explanation and uncertainty kind of overlapped within GradCam. You can see that the explanation themselves was looking at the face of the dog as well as at the feet of the dog. And it kind of makes sense, right? If it's a dog sled, you need to be looking at these two parts. But as soon as you look at the uncertainty, it kind of overlaps with the explanation. And this is the exact opposite of what we had before. Before, your explanation and uncertainty kind of was around each other, but it was not overlapping. While in this case, when the prediction is incorrect, there's a large overlap between the two things. And in GradCam++, it's actually the opposite. Before, you had a certain region on the explanation, but right now it's not as much. Like the explanation does not look at the dog sled, the feet at all. It's only looking at a particular dog, while the uncertainty is only limited to the small region over here. Yes, there is about green and yellow regions here, but red is the more heat map. That is where it's looking at as more importance. So it's not as visible. The overlap is different. Again, there's philosophical arguments to be made for both these things. At this point, I'm not saying one is better than the other. I'm saying that there is an objective metric that can be used to say one is better, or based on your preference, if one is better than the other, and so on. Same thing with signal to noise ratio as well. Higher the SNR of uncertainty, more is the dispersal. So if your prediction is incorrect, your network is less trustworthy. So it's looking at all parts of a particular image in order to make a decision, while it's not actually making that particular decision, while that particular decision is incorrect, essentially. So again, we're not, I just want to stress that I'm not saying that one is better than the other. I'm saying that this is a methodology that helps us to show whether one is based on your preference, if you want to use one over the other, and so on. So with that, I think we come to the end. Hopefully, I'll be able to do this within the next 10 minutes. I think 4 minutes until my original deadline was actually 12, but maybe I'll go about 4 or 5 minutes extra. It's just conclusions and future directions. The way I started was memes, and I just want to end with some few memes in that sense as well. We saw this before. Novel data, it packs like this kind of a 1-2 punch, because novel data is not available during training, but even if it is available, we really don't know how it fits in. And this is where we want to use this kind of inferential based robustness measure during deployment. We thought deep learning is very good in terms of robustness, but then adversarial images came in, and it's not always easy right now to try to understand what the robustness aspect is for a deep learning framework. While existing research in optimization in robustness usually deals with optimization, data collection, inference is not as well understood. We're not using inference as much. We just think that a network has to be as good as possible before we deploy it, but it's not always possible to get a good deployable architecture. We will encounter novel scenarios, and we need to have measures during deployment to see what we can do about it. Trained neural networks have a wealth of information. We usually think of it as you have a network, you pass it through the architecture, you get some result out out of it. But these days, with foundation models and prompting, we now know that there's a lot more underneath the surface. A network knows a lot more than we give it credit for, and we should be able to take it. This slide would have made a lot more sense if I explained image quality assessment, by the way. Unfortunately, I was not able to, but underneath the surface, we can actually get a better understanding of the images and distortion that exists. And I love the concept of explanation. I've always been working on it. But more and more you look at it, maybe we're not actually doing any kind of explanations. Maybe all we are doing is reducing this kind of uncertainty. And again, if you are an uncertainty person, then hats off to you. I think it's very good. But ideally, more research has to go in this direction. It's not just getting a good explanation, getting a good methodology for explanation, but evaluating explanation itself is very, very hard. And we should be able to evaluate explanations instead of trying to approximate it using uncertainty. Some key takeaways that ideally we want to take away from this is the role of gradients itself. So in all three parts, we had gradients as our starring figure. It was our protagonist essentially in different ways. Gradients at inference, it provides a solution to the challenges. We don't have access to the manifold at inference. We should be able to approximate that somehow, and gradients is a way for us to get that kind of it provides a mechanism for us to get that kind of a traversal within this unknown manifold. So gradients approximate Fisher information. They can be manipulated by providing some kind of contrast classes. It can be used to construct localized contrastive manifolds. So in most cases, it's going to be you don't know what your manifold is, but you can make small slight changes within the manifold, and that distance is essentially localized contrastive and counterfactual manifolds. They also provide this implicit knowledge about all classes. Again, extremely important. At inference, we assume we have one data point, one network, and we get some output based on that data point, which is not the case. If we just dig in the mechanism, there is a lot more available to us within the framework itself. Gradients actually are useful in a number of image understanding applications because it helps us in highlighting features. In the explanation part, it provides directional information for anomaly detection, quantifying uncertainty for these three things that we saw, and providing expectancy mismatch for human vision related explanations. Again, expectancy mismatch is the opposite of attention. Attention is where it's the sensing mechanism, but expectancy mismatch is based on a task that is in our minds. We look at a particular, so if you take two people and show them the same scene, their attention is going to be different. Reason being that their experiences and tasks are going to be different. They form this expectancy in their minds, and then they see a particular scene, and then they say, oh, this is not the same thing. There's slight difference between it. And this is, again, related to human vision system. This is related to like image quality assessment and human vision saliency, but we didn't go through this application. But essentially, gradients help us in trying to get, instead of attention, which is there, it helps us to get expectancy mismatch, which is a top-down process rather than a bottom-up approach. Future research directions that we should be looking at, test time augmentation. It exists, a lot of test time augmentation exists, but we want to make sure there's some kind of an intelligent test time augmentation. You don't want to make simple augmentations, see what the output is, and get results. There has to be some kind of intelligent way of doing it. Active inference, extremely important. You want your network to say, you want your net. So one way of thinking about active inference is that I give a certain object for recognition, and then the network tells me this is not a good angle. Why don't you move a little bit? Why don't you move 60 degrees and then show me the same image? And a network should be able to tell us that. Again, all of this needs to happen at the inference stage. We can't program a network to say X degrees, you need to ask it to move. It needs to be able to understand and plan these strategies out during inference. Of course, then uncertainty and explainability, label interpretation, and trust quantification. I've used the word trust, uncertainty interchangeably throughout the tutorial. They're not the same thing. Uncertainty is just one component of the concept of trust, and it's a completely different resultant out there. AI alignment as well. So we think of what AI alignment is from a reinforcement perspective, but reinforcement learning perspective. But AI alignment has to be there at decision-making process. So we saw the traffic sign, the stop sign. The fact that it was looking at the bottom left corner edge maybe is not aligned with how humans make their decision process. And the network has to be able to simulate this process. And the simple answer shouldn't always be that we need to add more data to see the results. We have to be able to look at it from the perspective of inference, what happens there as well. I think that is the last of the slides. And I think I'm 3 minutes above what I initially set out. But yes, this is the slide again with the slides that was there. Thank you. By the way, speaking for 3 hours was not as easy as I had thought it would be. Thank you. You can reach us by emails if you want, or I'll stick around for a few minutes if anybody has questions. I know there's like a online component as well, and I'll keep checking that if there's any questions as well. Okay. Yeah. Yes. Yeah. Yeah. Yeah, I'm not sure the answer. Yeah, training is not the way to do it for sure. Yeah, and I'm not sure of the answer. Like, if the goal is to get a good result, I think what network is doing is probably the best way of doing it, right? Because it's the only class. But in more safety critical applications, maybe it's more important to have like AI alignment with the human decision making process. I don't think it's a short solution that this has to be aligned. It's more for a particular application. I think it has to be aligned at least. How is the open question? That's very hard. I mean, simple way I can do it is by putting another traffic sign which has a bottom left corner. So it has to find another feature that this thing. But it's during training, it's never possible to intervene in that small capacity.
Yeah, you don't know which direction.
Exactly. Exactly. Oh, thank you. Thank you. Thank you.
Yeah, nice to hear. About this gradient for uncertainty and most of the
Yes.
like how the gradients
Yes.
but in that
So in explanation, we used it from the last convolution layer.
okay.
Then in the no, that's not explanation. That was the introspective learning part.
Okay.
Yeah, explanation was the last convolution layer. Introspective learning part was the last layer. Yeah. Okay. All the results and take L2 norm for all the layers, and then kind of take a mean of the entire thing. That's it. Yeah. Okay.
What I see is like some of this typical noise.
Mm-hmm.
It's more
Right.
takes some
Exactly. Yeah.
not necessarily to become correct design, but it's very
sure. I agree.
so just
Yeah. Yeah. I think based on application, you can actually say, oh, I like this layer for this, and so on.
So yeah.
Yeah.
So
it's,
this kind of thing.
Yeah, we did. I think we tried different kind of things. What we saw was that there's two things that was happening. One, if your initial training distribution was very good, then just the final few layers is more than sufficient to get results.
It means this kind of noise is
Yeah, exactly. In the distinct part, yeah, final few results. But if your training distribution and your network is not as good, then it's very hard. Exactly. Exactly. No, yes, thank you. Yeah.
I was
Okay. Mhm. Mhm. Okay.
So they
Okay.
in this way
Yeah.
backpropagation.
Say it using an LLM. Yeah.
Say
Yeah. Yeah.
reasoning.
Yeah.
What do you
I think that's definitely a very good and a required area of research, I would say. The challenge there is twofold, right? One is we are trying to interpret an unknown model using another unknown model. Like the LLM itself is something that is not easily known to us. And when you do something like this, there's this whole concept now called prompt engineering, where people are like, they're trying to engineer their prompts in order to do it. And a lot of times it's like just a shot in the dark, where you try something, you try another thing, and you keep on trying, and so on in order to get something, right? And while I think it is very important, it's if we want to get to the bottom of how it's being done, you should not trust what a network is telling you. And that was a goal when I talked about intervenability. That was the goal. Like, it's giving you an explanation based on something, yes, but maybe it's not something that it is trusting itself. So how do we know that it's the LLM is also doing the same thing? Because there's been a lot. I looked at something called this kind of a Snow White problem in LLM. I'm not sure if you've seen it. If you ask ChatGPT, which was the first animated feature film, it says Snow White. But it was not the case. A few years back, there was some other animated feature that had come out. And if you ask about that feature, it tells you that it was there at this particular time it came out. So it knows, it has complete knowledge. But it doesn't give you that answer because it's not able to reason the fact that one is before the other. Like, I forget the exact dates, but 1930 versus 1920. It doesn't know that 1930 is greater than 20, right? So the reasoning stage does not exist very well. And that is something that if you ask a network, it will screw around. So if, especially for anomaly detection, that might be problematic. Yeah. So, but again, I think it's very important to have that kind of a thing. Like, we have to keep on getting better LLMs, and we have to keep on getting the visual parts as well. So yeah, yeah.
Thank you.
Thank you. Yeah. Yeah, of course. Yeah. Thank you. Okay. 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 Yeah. Okay. Oh yeah. Please reach out. Yeah. Please. Yeah. Um, uh, 1 second. Let me just. Yeah, this is my number. So I was online, so I didn't want to. Yeah. So anonymous attendee, could you please repeat the questions from the room, as online attendees do not hear? I'm so sorry about that. Yes, I completely forgot that you can't hear it. Unfortunately, I think everyone's gone, and this was the last question, I guess. I'm sorry about not repeating the questions. Yeah. Yep. Okay. Yeah. Mhm. Yeah. Yeah, that was the introspection part. So there was a question in the room for the online attendees, where the question is about, did you try using introspection on the source data itself? And we did it for introspection. There's no difference at all on the source data. The results are the same thing. So if you had 76% accuracy, you would get 76% accuracy again, because gradients are not giving you any new information at this stage. That relationship between yi and y cap is the same when it's source data, right? And only when it's novel data is you have some new information that exists, which the gradients can give us. Oh, what happened? So the question is about, how do you learn this network? We take the source data, we get gradients across all, let's say, 50,000 images. And Okay. We get it across like 50,000 images. Yeah. So I can end the show. Yeah, I learn it across 50,000 images and I train an MLP. It's as simple as that. I take the gradients, I pass a single image. I take the gradients for that image by passing this one n, which is a confounding label. So let's say this is a 50 cross 10 matrix. I convert that into a 500 cross 1 vector. And I do it across all 50,000 images and train this MLP on the source data itself. And what we notice is that when you do it for a novel data, this network is giving you a more better generalizable and a calibrated result.
Okay. That's just percent.
That's it.
So,
That's it. It's the same thing. It's very simple. Actually, we didn't actually test using which loss. Maybe there's some losses get better, some loss worse, but just using cross entropy. Or I think this was MSE loss. I think the paper has this thing. It has MSE loss, I guess.
okay.
Yeah. Yeah.
So you should almost percent and average.
Yeah. We've tried it for ImageNet as well. It's the same thing. You get good results there as well. For ImageNet, you cannot directly use the this thing because this, instead of 50 cross 10, it's going to be cross 1,000. So the dimensionality is going to be very high. You need to use PCA. So we use PCA to bring it down to a very small size, and you can get results there. Yeah. But of course, the this works if your sensing network is very good. So the reason we show MNIST and SciFar10 is that they already have about 90% accuracy, right? So the sensing network is very good. The information you get out of it is good. In ImageNet, you have like, I think VGG was around 67%, even transformers around 80%. So you don't get as good, but that's not because the introspection is bad. It is because the network itself that is giving you this information is bad. So that is the catch there.
That is a huge problem that if we're up to 10%,
Yeah.
try, let's say, natural shapes like
no, I don't think we have tried that, but yeah, that's a good this thing.
And
actually, we well, not sketches, but we tested on this WIS-DA thing.
yeah, okay.
The cartoon versus animated versus this thing, real things. Yeah, for domain adaptation.
Thank you.
No, I think good. Yeah. And thank you to everyone online as well. I think that is the last of the session. I'm gonna stop sharing and stop recording as well. Thank you.